Welcome everyone. I'm Michael Gibbs. I'm joined by Mark Milovanovic, and today we're going to talk about networking for cloud computing. We're going to do some AWS networking training. We'll talk about what is CIDR or classless interdomain routing. We'll get involved in subnetting. We'll have a little bit of fun with variable length subnet masks. Now, networking is critical to anything. Want to design a cloud architecture? The foundation is the network. Want to design an AI architecture? The foundation is the network. Want to design an enterprise architecture? The foundation is the network, and here's the reason why. If the network's not right, nothing else will ever work. So the network is critically important. So together, Mark and I are going to work with you. Now, Mark and I are not new to networking. We're both Cisco certified internet experts, which is honestly, it's kind of a doozy of an exam to pass. I've been in networking for almost 30 years now. I like to say 25. It makes me feel kind of young, but I've been networking forever. Mark's been in networking, and he's also a CCIE for about a decade now. So we're going to have some fun here. Now, we'll talk about subnetting, what it is, how it works, how to do it. And, we're going to divide between Mark and I. I'm going to kick it off and talk for a little bit. Mark's going to get good and geeky with you guys. We have lots of fun. He's going to show you the work, and he's going to make sure that hopefully all of you by the end of the day understand subnetting. Now, I come from the medical world. So I like to know that people are there, that they're awake, meaning they're alive and awake, they're alert, and they're oriented. So give me a hashtag that says hashtag AWS Advanced Networking, and then I'm going to know that you're awake, alert, and oriented. And then we're going to begin, because I need to make sure you're awake, because we don't want to talk about something like subnetting and have you guys all sleeping there. So we'll make it fun. Mark and I will do the best we can to take some ugly math and make it kind of wonderful. Now, I'm going to tell you about some free things while we kick it off. Towards the end of the month, we're going to do a completely free AWS Advanced Networking Bootcamp. And the AWS Advanced Networking Bootcamp lacks a lot of networking. I wish it didn't, but it does. So a couple of things. We're going to give you more than you need to know in the AWS Advanced Networking. It's going to be completely free. It's going to be taught by, in some way, shape, or form, by 3 Cisco certified internet experts, as well as a Cisco certified network professional that have together, 60, 70 plus years experience in networking, which I'm excited about. We're going to do a free BGP workshop prior to that AWS Advanced Networking. So today we're going to cover the subnetting, the IP addressing piece, some of that. Then we're going to do a BGP workshop, and then we're going to do a completely free AWS Advanced Networking. Now, hopefully we've got people from all over the world. I see a lot of people in the US, see lots of people in Canada. I know we've got some people in South America. I know we've got lots of people all over Africa right now, which is great. We've got some people in Europe, the Middle East, and Asia. So we're going to have some fun on our international thing here. So I'll kick it off, and then we'll begin. Before we begin, Mark, do you want to say anything?
I just want to say welcome, everybody. It is a real pleasure to be here and an honor to have you guys join us. Take a little bit of time out of your day. Hopefully, by the end of the day, you'll not be intimidated anymore by subnetting. I know that is always a very intimidating subject, especially if you're trying to go towards a certification such as the CCNA. But trust us, when you see it, we'll show you the work, how it is done, and then throughout, we'll sprinkle some ways on how you can accelerate some of the math. But just be assured, if you can do basic addition and subtraction, and you can spot patterns, this is going to be a piece of cake for you. So I hope you guys enjoy it.
Absolutely. While you're here, if you want to give the video a like, if you're not a subscriber, please subscribe. We do a lot of free training on this channel. And please invite a friend or send people the recording after the fact. A lot of people need this, and I know Mark and I will make sure that we can explain it as simply as possible. So what are we going to talk about today? We're going to talk about what is subnetting, and of course, we'll talk about why we need it. Then we'll talk about classful IP addresses, which we really don't use anymore, but it's kind of critical to understand these to get into the classless addresses that we'll talk about. And CIDR is all about classless interdomain routing or classless addresses. Then we'll talk about what goes into subnetting. And then Mark's going to teach you how to subnet. And then we're both going to teach you how to supernet, which is going to be critical for your architectures to be stable, because you're going to have to do something called route aggregation. We'll get to it. Then Mark is going to walk you through some subnetting and supernetting practice. We'll talk about some subnet planning and even subnet design, and we're going to get our hands dirty, geeky, and have a tremendous amount of fun. So what is subnetting? Subnetting is really the process of taking an IP network and breaking it into smaller components. Now, I'm from Greece. We eat a lot of pizza in Greece, Italy, lots of pizza, you know. So it's kind of like taking your pizza, like a whole pizza, if you're familiar with pizza, and chopping it up into pieces so you can feed your friends and not waste any pizza. Now, you wouldn't give your friend a whole pizza. You might give your friend a half of a pizza. And if you've got one pizza and 3 friends, maybe you divide it up in thirds. And that way everybody eats pizza. So, this is very similar to that, and we're going to walk through it. So why do we have to subnet? Well, it's all about conservation of IP addresses. When we deal with IPv4, which is still what we're really using, even though IPv6 has been around for like 20 years now, we really only have 2 to the 32nd power minus 2 in terms of number addresses. And while we've got a couple billion addresses, it's not that much. And why is it not that much? Well, you got to look at it this way. There's 7+ billion people in the world, right? And how many of these people have a computer, a mobile phone, a tablet computer in their house, cars that are IP enabled, refrigerators that are IP enabled, even some people's washing machines will send them a text message that says your clothes are ready. And every one of these devices needs an IP address. So as you can tell, we ran out of IP addresses a long time ago. Now, every interface on a router or a server, for the most part, is going to be a different subnet or a different network. And what does this mean? It means if you've got a router which has 100 interfaces on it, you need 100 different subnets or networks on that router. You got a server with 4 network cards in it, and they're connected to 4 different parts of the network. That server is going to have 4 different networks on it. And this is where we're going to run out of IP addresses if we're not careful. Chris, if you could share my slides, please. Okay, so here's a situation where we're going to take 4 different Class A networks. The 1.0.0.0/8, the 2.0.0/8, the 3.0.0/8, and the 4.0.0.8. Now remember what I said, every interface needs to be on a separate subnet. So if we took these 4 basically IP subnets, which happen to be Class A addresses, we'd be using 64 million addresses on a router. I gotta tell you, we can't put 64 million addresses on the router, and here's the reason why. Once we get above approximately 256, max 512 addresses on a subnet, we actually run into trouble, and basically the subnet will become almost unusable. And here's the reason why. All of us have computers, and our computers do things called broadcast. And the broadcast really tells our computers how to reach things we don't know. When I map a name to an IP address, we do an ARP who has the MAC address, and that's a broadcast. Well, our systems send these broadcasts to find Windows and Mac computers that are next to each other. Switches send unknown broadcasts out all ports except for the one it came in on. And if we're not careful, all these devices in a subnet will just broadcast. And it'd be kind of like listening to a radio without listening to 50 different channels at the same time. So we must subnet. Now let's look over here where I'm going to do it a little differently. So here I've actually subnetted it. Let's say this router has 4 links, and each one is a wide area link, or basically a virtual cable between point A and point B. Now there's only 2 possible IP addresses on both sides of the cable from point A to point B. So in this particular case, I subnetted it down. So instead of using what we had here, which was 2.0.0/8, and I burned 64 million addresses, through careful subnetting, I'm able to use 16 addresses. Chris, we can pull that slides down for right now. So now you know why we're talking about subnetting. We have to. We can't waste 64 million IP addresses on a router with 4 interfaces. What would happen if we had a router with 10 interfaces on it? Or would we honestly burn 16 million addresses per interface for 10-minute interfaces, which is 160 million? Pretty quickly, one company would reuse all the IP addresses for the entire world. So that's not going to work. So we have these concepts of classful addressing. And classful addressing was what we used to use back in the 1980s, late 80s, early 90s, when we had the DARPANET and the internet was really only used for educational research and military purposes. Then we used classful addresses because nobody really thought the internet was going to become anything. I mean, you had a couple military facilities, a couple universities that were connected together. IP addressing wasn't a problem. And yes, my Mac has all kinds of funny AI that generates all kinds of things in the background. It is what it is. So, in those days, we used classful addresses. Now, when I started in networking in the late 90s, we no longer use classful addresses because we wrote around out of them. But Chris, share my screen real quick, and I want to show you the actual address classes that actually exist. We have the Class A addresses, which are really anything where that first octet, 1.0.0.0 or 1 all the way up to 126.0.0.0/8. Now that /8, Mark's going to get down and dirty on the geekiness of how it's actually counted with the zeros and ones converting binary to decimal numbers. But anyway, understand in a completely unsubnetted environment, anything from 1 to 126 in that first octet will have a subnet mask of /8, which is 255.0.0.8, and 16 million addresses. Now, the next set of addresses that were specified were the Class B addresses, and they were everywhere in the 128 all the way to 191. And this was that 16-bit subnet mask where it's 255.255.0.0. And, here we've got, quite a bit of IP addresses, about 65,000 in that particular network. Again, far more than we could ever use due to broadcast problems and other challenges. So there's that. And then we got into the Class C addresses, and you've probably seen most of them because this is what most of your PCs are going to have on them if you're in your home. You're going to be in that range of 192 to 223. And here's where you're going to get that 24-bit subnet mask, the 255.255.255.0. We'll give you some guidance on what kind of subnets to use later. And then we've got my favorite, which are Class D addresses, which are used for IP multicast. And I was an IP multicast architect a long period of time. That's the 224.0.0.0 to 239. And, that's used for me to send one thing to many users. So if you have IPTV enabled from your cable company, typically what happens is you take the video source, which often comes from a satellite, you plug it to a video encoder, that turns it into a multicast stream. And when you want to watch a TV show, you just subscribe and you get it. And if you don't want to watch that TV show, you unsubscribe or leave the IP multicast group, and you no longer see it. Now, there's also the concept of these Class E addresses, but guess what? There's no such thing, at least in terms of use of Class E. They're experimental. They've never really been used for much of anything. So keep that in the back of your mind. So I wanted to show this to you. Normally speaking, our Class A addresses have 8 network bits and 24 host bits. And that's why we've got 16 million IP addresses, because it's 2 to the 24th power minus 2. Mark will get you good and geeky on that one. And, in that Class B, we basically have 16 bits of networking and 8 bits of host, which means we've got about 65,000 addresses. And with that Class C, you can see it's mostly networking bits because it's 255.255.255.0, and we only have 8 host bits, so we now have 2 to the 8th minus 2, saying 254 addresses, except for the cloud, where things are going to get a little funnier, and we'll talk about that. So when we subnet, let's say we had a Class A. The Class A naturally only had 8 network bits, and it also had 24 host bits. So subnetting is honestly playing with the networking and with the host bits. So we'll ultimately have subnet bits, which will effectively become more network bits and less host bits. That's really what's going on. We're taking these networks, these big blocks, Chris, you can stop sharing, and chopping them into smaller blocks. So that's really what we're talking about. We're talking about an environment where we've got 32 bits. And either we can push these bits to the network side and have more networks and less hosts per network, or we can push them to the host side and we have less networks and more hosts. But we got to remember, we can only stick so many hosts in an environment. It's kind of like going to the local grocery store. Maybe that grocery store has the capacity to have 300 people in it. But if 1,000 people get in that grocery store, everybody's going to be pushing each other, trying to go from point A to point B, there's going to be lines or queues all over the place because it's the equivalent of having a subnet with too many hosts in there. It's blocky, there's too much broadcast traffic, and it won't work. So, Mark, why don't you start getting into the metrics here for us?
All right, so what we're going to start off now is to be able to associate something we already know with eventually working with how computers understand numbers. And that's going to be the binary system. So I'm going to first share my screen. We'll talk a little bit about decimal system. I'm going to get some feedback from you all too to make sure that we all understand it. So let me share my screen here for a second. And let's take this one. All right, give it a moment. And if you guys can all just write in the chat, if you see my screen, that'd be helpful. Just if you can confirm, please. All right, fantastic. All right, so when we talk about the decimal system, it's a system of how we count that we're familiar with. So if I was to represent to you all the number 587, it would be something that is natural to you. But when we originally learned this type of numbering system, it was broken down to us in various ways. One of them was that each position of a number had a basic value. In decimal, we use the base of 10. And we'll get into that, what that means. But when we originally learned this, we started breaking up per position. So the way it would work, we would be told that we have 5 100ths positions. Then we would have 8 10ths positions. And then finally, we would move on to 7 ones position. And if we do the quick mental math on this, 5 times 1 is 500. 8 times 10 is 80. And 7 times 1 is 7. So in the end, we've broken it down. And when we add it again, we'll come to 587. So that is very natural to all of us all around the world. So the way these numbers actually came about is, as I mentioned, we had a base 10 system. So what that means is that every column that we have of values is going to be based on 10 values that we can create numbers with. So I'm going to just write these down here, and then we'll go through them. It's going to be 10 to a power of itself. But the way you would look for it, if we have base 10, we would have values 0 through 9. So within this particular spot, I can have 0 through 9. Those are my values that I can work with. But before we get into how this is represented, let me ask you in the chat as we go through this. What is 10 to the 0 power? Let's just start off with this. Just some basic math, just to warm up the blood a little bit. I'll give you a couple more seconds. So what is 10 to the 0 power? All right. Fantastic. Is 1. Perfect. All right. What is 10 to the first power? Again, I'm just doing this on purpose so we can warm up the blood a little bit as we continue. So what is 10 to the first power? It is 10. Fantastic. All right. Let's go to 10 to the second power. So we're looking at 10 times 10. What is 10 times 10? Fantastic. All right. And then finally, let's do 10 to the third. So what is 10 times 10 times 10, or 10 to the third power. You guys are rock stars. Yeah, very much. Yep, it is 1,000. Fantastic. So this is the way that we base our system, the decimal system, and how we came up with the different values across the different columns. So it's very basic math. It is something that we grew up with, something that we were taught, something that is so automatic that when we just see a number now, like 587, we don't even go through the process anymore of dividing it up in these different columns as we have. So is everyone so far clear on this? Before we move on to another concept of the values and how we create the different numbers in decimal. What do you guys think? Everything so far clear? All right, fantastic. So let's do this. All right, so I mentioned we have values 0 through 9. So the way that that would work is we would start off with 0, even though many times we don't actually write the 0, but the 0 is there. And we move forward. So the next would be 1, 2, 3, 4, 5, 6, 7, 8, and then finally 9. Let me delete this. And that is the combination of numbers that we have available. So when we move from 0 to 1, we increment by 1. From 1 to 2, we again increment by 1. From 2 to 3, we again increment by 1. So this is all still very basic math. We've all done that in grade school. Should be nothing complicated. So now my question is going to be to you. I finally arrived at 9. So I'm still in my first position, right? This 2 to the 0. And I'm trying to move, I'm sorry, not the 2 to the 0. I'm jumping ahead. I mean the 10 to the 0, and then eventually a 10 to the 1. So once I get to 9, I'm going to be incrementing by 1 again. So how would I write 10 the way we understand it? And I give you a little hint. If you ever seen an old school automobile odometer, you'll notice that when it gets to the maximum value, it rolls over, adding a position, and it resets the far right position. So the way that that would look for us, and we're going to delete all this, is that our ones position or our single position gets reset to 0, and we add the 1 to the next column. And that's how we create the number 10, or 1, 0. And of course, if we kept going, we would now increment again on our far right number. This would be then a 1, exactly a 0 carry. The second column will keep the same as 1. We'll increment again by 1 over here, which brings us to 2 and 12. And then as we keep going, we'll eventually get to the number 19. And once again, what do? If we increment, we'll reset to 0, correct? And then what happens to our second column? Do we keep it at 1, or do we add a third column? What do you guys think? We know we have to reset the far right column. Correct. Yep. Anyone else? What happens to the second column? We're back at 9. We reset it to 0. We change it to 2. Correct. All right. Let's do that then. This will be 2 and then 0. And then guess what? We'll just repeat over and over again until eventually we get to the point where we'll have number 9 and 9 in both the first, which is the ones column, and then the second column's the tens column. So now comes the question. And just so everyone is aware, we're going through this exercise on purpose because once we go into binary and we have some larger address spaces, such as what used to be known as the classful A-B range, this will make a lot more sense and will be very useful. But let's say here, I'm at 9 again. I need to increment this number plus 1. It's going to switch to what number? What are we resetting this right-hand column to again? To 0. Okay, let's add a 0. And what happens to this number now? To the second column number? It gets reset to 0, correct? And then what we do is we add a third column, which is going to be the hundreds position. And that gets incremented from a 0 to a 1. So would everyone agree so far? This is very basic. We all can get a hang of it. Might even be a little mundane and boring going through such an exercise. But does everyone remember this from grade school or some variation of this type of teaching in regards to how the decimal system functions? Yes, no? Everybody clear on it? Okay, fantastic. All right, so the next exercise we're going to do before we actually get to the binary system, and you'll see, no, you don't get it. Okay. As we go further, you'll see why I'm going through these simple exercises, because it's going to be important once we get to binary. Right now, we're dealing with a rather small number. Now, the only thing that can happen here in regards to as we increment from one to the other is that you can keep writing until you run out of whatever you're writing on. If that's a computer screen, or it could be a board or a piece of paper, whichever it be. When we start dealing with actual binary, and then what we're going to focus on is IP version 4 addresses, we're going to have 32 different columns. So we want to warm up and get an idea of how this carryover is actually done, because it's going to be similar, but yet it's going to throw us a little bit for a loop because of we're not using a base 10 system anymore. But we'll get to that.
All right, Mark. So let's take a break, a moment or so to think about why we did this before we actually go to the next phase. So why was Mark teaching you base 10? We've been working in this for the last, all of our lives. The key is from base 10, we're going to have to go to a base 2. And, one of the reasons Mark talked about going from 0 through 9 is, at least from people in America, they think that we start counting from 1. Now, I'm from Greece. Mark is from the Serbia, Croatia area. So in Europe, we start counting at 0. But in America, we start counting at 1. So when we get into binary and we have 2, it's either going to be 0, which means off, or 1, which means on. But if we didn't go through that base 10 and you didn't understand how we go from 0 to 9, and then we move the decimal 1 and a 0, and then how we go to 100 or 1,000, it'd get fairly complicated to go down these binary numbers. So now Mark's going to take that math, which hopefully was pretty straightforward, and now we're going to get into the 0 and 1s, which is kind of like was it base 2? To me, it was always
Mhm.
taught in binary, and so there's that. So are you all there? Do you all get it before we go to the next part, fundamentals wise? If not, ask a question because we want to help you. Otherwise, we're going to go dive deep into we're going to start having fun with the geeky subnetting math. Does everybody get it so far? Let us know in the chat box.
Yeah, if you have any questions about this process right now be time to ask, because once we move on, we're just going to keep layering knowledge upon knowledge, and then we'll eventually get into the exercises on how to dissect the binary and actually perform the conversion.
And to be fair, it may take a couple of times to go through this.
Mhm.
At some point, it actually becomes so natural to you that you'll actually just see the subnets in your head. But it's not going to happen today. You may have to watch this twice, 3 times, and it's okay. It really doesn't matter as long as you get it in the end. So I'll let Mark get back to what he's doing. I see a whole lot of yeses here. I see a let's get geeky, which is something that I always love seeing. I don't get geeky very often as an architect because it's so much business work. But every once in a while, I can return to my tech roots, and it's kind of fun and it's kind of exciting. So, Mark, I'll go back to you. It looks like all clear from all kinds of people coming. Yeah, we got our propeller hats on for this one. Wait till you see when we do the BGP workshop and we talk about the BGP messages and how they work, and Mark demos it. We'll get geeky, but you know what? It's good geeky. It's good skills. These skills will truly enhance your career. Mark, over to you again.
Yeah, and so that everybody understands, it's very similar to when you were in school. Your teacher always asked you, show me your work. And it wasn't necessarily for the benefit of the teacher, but it's to help you understand the behind the scenes, the man behind the curtain, so to say. Because once you get into the workforce, you're generally going to have something that's going to aid you in running these computations. You're not just going to always be sitting there, especially as the hosts become larger or the networks become larger, you're going to have spreadsheets that help you with the calculation. But this is good for tests. If you're going to take an exam like the CCNA, this is going to be fantastic as you practice this for interview in case somebody wants to question you in regards to your knowledge in subnetting and the binary to decimal and decimal to binary conversion. And that's why we're doing it the long form hand. And I hope as we continue, especially as we get into breaking down and subnetting and supernetting the different addresses, that you get a piece of paper, or if you want to have a notepad, and that you follow along and practice it. And that's going to help you a lot. So if we want to go ahead, if you want to share my screen back, Chris. Okay. So that was the base 10 or the decimal system. Now, when we look at computers like to speak in what we call binary, meaning there's only 2 possible solutions. So it's going to be a base 2 system. For us, this means that a computer either sees a 0 or it sees a 1. Now, many times what you'll see people tell you is that the way we should interpret these zeros and ones before we actually give it decimal values is that the 0 means off and the 1 means on. So that's the way you also want to try to keep a track of it. 0 means, in most cases, ignore it. There's some cases, of course, when we come to access control lists, so other mechanisms we use for routing, that means something else. But in this case, 0 means ignore it, and 1 means you want to pay attention to it. So off and on. So let's remove this. Right. So since we only have 2 possible solutions, let's write them down and take a look at how that would look for us. So as I mentioned, we have the possibility of 0. So just as we did with the base 10, if I was to increment it, I would get a 1. Now, again, I'm going to ask you all in the chat, what happens when I need to increment this 1? Think back on what we did with decimal. And type it in the chat. What would happen to the 1 here? Correct. Yep. Sin, you're correct. We would reset to 0, and that would be our other option. And then eventually, what would we have? We would have this option as well. So we got 0, 0, we got 1, 1. Actually, let's keep it this way. Then we have what? We have 1, 1, and 1, 0. Right? So we don't have many possibilities. But just like in our decimal system, we're not actually constrained or limited by just 2 columns. We can increase these columns as much as we need. And that is something that we also do eventually with IPv4. IPv4, what you'll see is many times we'll write that it has 8 distinct columns. So this is 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7, 8 columns. So that is a chunk, what we call an octet, just 8 bits, 8 columns, you might refer to them. And since we mentioned we're using the base 2, we'll start off the same way we would with the decimal system. But instead of 10 to the 0 power, we'll write it as 2 to the 0 power. So we're going to work through all of this together. What would you say is 2 to the 0 power? What is the value that I would assign to this? And now we're doing basic math. So we're thinking simply, how do we translate 2 to the 0 power? Go ahead and type it in chat. Yeah, I see a lot of ones. Fantastic. Yep, that is correct. All right, so the answer to that would be 1. And then this also, what we just wrote here, is going to be our decimal value. Okay, just so we know. That's going to be our decimal value. Yep, you all got it. That's fantastic. So as you can already see, it's not as complicated as it first seemed. So let's move on now to the next column and see what the math tells us. So that's going to be 2 to the first power. So what would be our result or our sum there if we were to do the math? 2 to the first power. Okay. Awesome Singh, 2. Yep. Michael, 2. Yep. Navneet, fantastic. Idris, awesome. You guys got it. It'd be 2. Fantastic. Anna, yep. So let's write that down. 2. Now, what would you say is 2 to the second power? So now we're talking 2 times 2. What would that get us? All right, awesome. Yep, that's 4. And I want you all to keep something in the back of your minds, and you're going to hear me this quite often. As we go through the lesson today, I want you to pay attention and see if you can notice patterns, because that's going to be very important in making your life easy when it comes to subnetting, is noticing patterns and then adjusting to them and using them. So let's move on to the next column. It's 2 to the third power, right? So we said this was 4, and now we're doing 2 times 2 times 2. You all tell me, what is the result of 2 times 2 times 2? Or 2 to the third power? All right. You guys got it. Fantastic. 8. All right. Now, I'm going to stop briefly here, because I just mentioned patterns to you all, and you guys are awesome. This was fantastic. If we're looking at all these numbers now, can somebody tell me if there's a pattern that emerges? What is it that you notice? What do you notice between these numbers? We went from 1, we went to 2, we went from 2 to 4, and 4 to 8. All right. You're doubling. Yep. You're multiplying by 2. All right. So in that sense, would you not say, now that you've noticed the pattern, and I'm going to write again, the powers underneath these columns. So without having to actually sit there and do this type of math, since we're just multiplying by twos, or we're doubling every number that comes up, can somebody tell me what 2 to the 4th power is? This thing just gave up all the way. Thank you, buddy. All right, so 2 to the 4, can we all agree it's 16? Go ahead and type it in the chat if you agree with that math. 2 to the 4th power is 16. All right. Awesome. All right. What is 2 to the 5th power? Two to the 5th power. I'll leave it up to you guys. Get your juices flowing. 32. Fantastic. You guys are on a roll. All right. So far, so good. Now, what about 2 to the 6th power? So that's going to be 2 times 2 times 2 and so forth. What will we get on that 6th bit, so to speak? 2 to the 6th power. Yep. Yeah, you guys are spot on. It's 64. All right. Looks like everybody agrees. And then finally, let's move on to the last bit, our 8th bit, which is going to be 2 to the 7th power. What will be our final decimal value when it comes to this octet, these 8 bits that we're looking at? We went all the way from 1 to 64. What would be our final bit value from 2 to the 7th power? Correct. Easy peasy, guys. You see that? 128. So did anyone find this right now to be complicated? Or do you guys think this is something you are going to be able to do in your sleep in regards to just being able to double the numbers? Yeah. And Kevin, we'll eventually get to how you came up with the 255. We'll get to that and how that is done. Okay, fantastic. You guys are great. All right. So in this sense now, we know what our decimal values are in relation to the binary system, the zeros and the ones, as we move from right to left. So the math itself, as you'll notice, is not very complicated. So if anyone has any questions before I move on, and we're going to do a little bit of an additional exercise on how to do the actual conversions, please go ahead. And Chris, if you want to put me and Mike back up. So does anyone so far have any questions? Because I'm not that great at math, and even I was just amazed that I was capable of doing this. We're all good. All right. So as you see, just like in decimal, we move from left to right, we increase or we add columns of positions so that we can be able to do our calculations. Now, I picked 8 bits there for a reason. And that is because when we work with IPv4 addresses, there's going to be a specific value that these, or specific size that these IPv addresses are. Now, if we're dealing with version 4, we're dealing with 32 bits, which means we can have 32 columns where we can actually place zeros and ones into them. So that we're going to see that's going to be quite large. I'm going to show it to you. And then we have even something larger, and that's called IP version 6. Now, we're not going to get into that, but just be aware that is 128 zeros and ones that you have fun to play with. So I hope you guys liked it. So let's do this. I'm going to pick a number, which I already have ready, and let's take a look and see if we can do a conversion from decimal to binary and then reverse it before we actually go into performing any further subnetting and taking a few more questions. You think that would work, Mike? Okay.
I think that would be absolutely fantastic. Sorry, we've
Okay.
got someone behind the scenes muting and unmuting microphones. It's we have to do it with this new
No problem.
platform.
Okay, fantastic. All right, Chris, if you don't mind, go ahead, share my screen, and we'll go on to actually doing some conversion. So let's see if I can find the row. Sure. Let's move this one. All right, let's increase it. So as you can see, this is the same table that we were just, let's see, why is my pen not working? Is it not? Give me 1 second, guys. I'm not sure what's happening to my pen. All right, fantastic. So as you can see, this is the same, and just do me a favor, ignore this for right now. We'll get into that. But I want you to focus on these values. Okay, and what I want you all to do right now, before we get into the conversions, I want you, if you could, take a piece of paper out and create this table. I want you to write down and create this table. I want you to have it handy. I'm going to give you guys about, let's say 30 seconds to create it. And then we'll go briefly through one more exercise, and then we'll do the conversion from decimal to binary, and then we'll go back. So about 30 seconds. If you don't mind, let me know in the chat when you're ready, and then we'll proceed. And unfortunately, we don't have any Jeopardy music. All right, fantastic, Victor. All right, let's give it a couple of more seconds here for everybody to create that table. Yeah, there you go. Thank you so much, Chris. All right, I think we can stop the music, Chris. Thank you so much for that. Appreciate it. Okay, now that everybody's ready and has the table, we're going to go through one exercise because I want to be able to associate something you've done in real life with what we're about to do with the binary system. So let me give you guys this scenario. Imagine you're going to the store and you'll want to purchase something. And let's say it costs you, let's say $9, and let's pick $9.59. That's what it costs you. That's the price of the purchase. Now, you're about to get to the register and you look through your wallet. So let's assume you have cash, okay? So no cashless society yet, but let's say you have cash. And you notice that you have a $10 bill. That's what you have. We're going to use American currency because it might vary a little bit on what type of bills you have, including coins. So we're going to look at that. So initially what you're going to do, you're going to be like, okay, I have $10 and it's going to cost me $9.59. So you start doing mental math and you figure out, okay, I have $10, and I need to figure out what my change is going to be. So you're going to do, okay, 9 to 10, that gives me 1. I carry the 1. 6 gives me 4. I carry the 1 again, which puts this to 0, which carries the 1 and 0. So you figured you should get a cash back of 41 cents. Can anyone in the chat please make sure that I did math correct on this? That we should get back 41 cents? And by the way, I don't want you using a calculator. Try doing this by hand. That's really where the exercise comes in. As you get better doing all of this, you'll notice, as I said, the patterns, you'll get quicker at it, and you start doing this in your head. All right, so correct, incorrect? It's not supposed to be 41 cents? Is my math off?
No, 41 plus 59 equals 100. You got it right.
All right, fantastic. So we got 49 cents. So I'm going to use the coin option that we have in the United States. So meaning I'm not at the register, I give them a $10 bill. I'm going to expect back to that from them 41 cents, preferably in the most efficient manner with the coin or the coin value that they have available. Generally speaking, in the United States, that's going to be 25 cents. We're going to have 10 cents. We're going to have 5 cents, and then eventually 1 cent. So what I'm going to do is I'm going to look at my coin bank now, and I'm going to think, which coin can I use to get the closest to 41 cents? So what is it? What would you pick out of these options that we have? Which option would you pick to get me the closest to 41 cents? In the most efficient manner, think about that. I got 41 cents. All right, I'm seeing 25, 25. All right, so 25. Let's go with that. So I'm going to say I use 25. I'm going to place a 1 below it. On the side, I'm going to say I'm not being owed the 25 cents anymore. So I'm going to subtract it. So what would this be? So 5 to 11, that is 6, if my math is correct. We carry the 1. 3 minus 4 gives me 1, which leaves me over with 16. Is that the same results you all got when subtracting 25 from 41? Is 16? Okay, if it is, and if not, there is a little cheat way for me of doing it, just so you know. We'll maybe use it in the past. We'll later on. 41 minus 25. We'll do equal and 16. I know that's a little bit difficult to read. So I know my math is relatively correct then. Okay, so I used up 25 cents. Next, I still have 16 cents left over that I need to get back. So what is the next coin that would get me the closest to 16? I need 16 cents back. So what's the next closest coin, or the largest coin, you might say? Okay, I'm slowly seeing a trickle in. 10, 10. Idris, output. Okay, fantastic. Let's go with the 10. Let's make sure we mark it down that we're using the 10. Let's also subtract it because, we're not being owed anymore. Math is going to be nice. 0 to 6 was 6 minus 0 gives us 6. And 1 minus 1 gives us 0. So we're left with 6 cents. So I'm going to just briefly speed this up because I've already seen some of the results. We would next use the 5, which would be 6 minus 5, which will leave us with 1. And then since we require 1 more cent over, we would go back to our coin purse, take the 1, subtract 1 from 1, which would get us eventually 0. So does this process make sense so far for everyone? And let me know if you all have at one point or another actually gone through this. I know today with credit cards and everything, not all of us always carry cash on us, but does everybody understand this concept of how we go about being efficiently able to match based on what we have available in our, let's say, coin purse, or if you want to say we're borrowing, or whichever verbiage you want to use? Okay, fantastic. Now, let me tell you this. Since you know how to actually give cash back, since you know how to add decimal values to binary columns so that we know what they mean in human terms, you already are on your way and know how to actually do the conversion from decimal to binary and from binary to decimal. So let's take a look and see if we can figure that out together. Let me go ahead and delete or remove all this. All right. And our goal is going to be by one, we're going to go through these decimal values, 192, and then we're going to go to 168. We're going to go to the decimal value 1, and then eventually 100. And what we want to do is, and I don't want you focusing so much on this yet, so we'll remove that. And we're going to convert them one by one into binary, okay? So we're going to start off with the number 192, okay? And let's see if we can do this, centered. Now, if I have 192, and thinking back to how we actually asked for money back, my first question is here to you. Let's write it down, 192. Which coin, if you want to think of it this way, would get me the closest? And I apologize. Let me do one thing because I don't want to confuse you all. Let's remove this entirely. All right, let's do it that way. That's probably a little bit better. So which one or which coins can we start off with that will allow us to get the closest to the number 192 of these? Which one would you pick? Think back to the example we just worked through. Okay, Victor, just one number. Start off with one number. We're gonna have to pick our first coin, not two. Just start with one. Otherwise, it is perfect what you wrote there. All right? Adva, Mohammed, perfect, guys. Yep, 100 and yep, Anna, fantastic. 128. So if you remember, I said 1 means on, which means pay attention, and I said 0 is off or ignore. So if I only have the 0 and the 1, what number would I place in there if I want to pay attention to the decimal value of 128? And I'll give you guys a hint. We only have the option 0 and 1. Okay, and I'll leave this 0. So this means off, and this means on. Okay. Yep, you guys are great. So let's start with 1. Okay. So now that I have that, we go through the same exercise again. I'm going to remove or subtract 128 because I'm not being owed that anymore. So 8 to 12 is 4. We carry the 1, which gives us 3. 3 minus 9 gives us 6. And 1 minus 1 gives us 0. So I'm left over with 64. That's my value that I have left over, 64. Everybody agree with me so far on this? And just so you all understand, I'm asking for confirmation because I can make mistakes, and it also gives you some practice as well to do the extra math. Okay, 64. All right. So what is the next coin that I would want to use that would get me the closest to 64? So I have left the value of 64, of 32, 16, 8, 4, 2, and 1. So what would you guys pick? $64. Fantastic. Right? We denote it by adding a 1 so that we know that we want to pay attention to it, that it's on. I hope nobody disagrees to that. Then we'll go back through our usual exercise where we're not being owed the 64 cents any longer. 4 minus 4 gives us 0, and 6 minus 6 gives us 0. So what that means is we're done. Nothing else is owed to us. So what does that mean for the remaining 6 bits here? These remaining 6 values. What do you guys think? What should we do with them? Referring back to this idea. What should we do to these values here? Zeros. All right, let's go ahead and do that. We'll add 0 here, 0 here, 0 here, 0 here, 0 here, and 0 here. Turn them off. Yep, perfect, Brian. So can somebody let me know in the chat, have you ever before this done a decimal to binary conversion prior to this exercise? And if you haven't, please let me and as well as everybody in the chat know if you found this horrifically difficult, or if you believe you can probably do this in your sleep going forward. So again, not too difficult, right? All right, fantastic. So that leaves us with, we knocked out 192. Let's move forward and let's go on to the next number because we're going to convert them all. And then what we're going to do is we're going to write them out. So our next number is going to be 168. Okay, so 168. Let's start off with that. Let's write it down here as well so we can do the math. Let's see if we can. Right. Okay, so same exercise again. I have the decimal value of 168. I want to convert it to binary. What is the closest coin that would get me to 168 out of the ones that I have available? The different columns, the different coins. 128, 64, 32. Okay, 128. That's correct. 128 does fit into 168. So what we're going to do is we're going to turn that bit on by designating it with a 1. And then what we're going to do is we're going to subtract 128 from 168 because we want to see what is it that we're left over with that requires us to go back into our coin purse and figure out what else we can apply. So 8 minus 8 gives us 0. 6 minus 2 gives us 4. And 1 minus 1 equals 0. So we're left over with the value 40. Same exercise again. What coin allows us to get the closest to 40? What would you guys say? The next coin. Can we use 64? Okay, I see everybody writing 32. So we know we can't use 64, but we can use 32. Yep, perfect, guys. You get it. So let's subtract 32 from 40. 2 to 10 is 8. We carry the 1. 4 minus 4 is 0, which, and I'm sorry about that, this support, let me just remove it. It's ugly. All right, so it leaves us over with an 8. Does 16 fit into 8? I would say no, so we'll add to 0. What about the 8? Does it fit into the 8? Does that work? Can I get 8, the value 8 back? Anna, perfect. 8. Ben, yes, fantastic. Yep, so 8 fits into 8. So let's do this before we forget. If you're doing this on a piece of paper, make sure you also turn the bit on by adding a 1. And just so that we're thorough, let's take 8, subtract it from 8, and we're left with 0. All right, so it looks like we're done. And again, just to reiterate, what happens to the remaining coins? Do we pay attention to them? Do we ignore them? And how do we designate it? Let's go one by one. What do I do with the 4? All right, 4 is a 0.
On that previous question about the 8, you had about
Yeah.
50-50 saying yes and 50-50 saying no, that you could get 8 out of it. I just
All
wanted
right.
to let you know I was keeping an eye on the chat box there. So
Got it. All right, so let's do this. Thank you, Chris.
Yep.
For everybody in the chat, those that thought or wrote in that I cannot use 8, or you didn't understand why 8, please type it in, and let's see if we can address it, because this is crucial before we move on to any type of subnetting, that we understand this process. So for those that thought that I can't use an 8, even though I had 8 over, why did you think so, please? Let me know. Okay, you just didn't understand why 8. Okay, anyone else besides Mohammed? Any additional reasons why they thought they couldn't use 8? All right, so let me explain why 8 and why we're going from left to right. When we initially gave the example that we went to the let's say grocery store, and we bought something for $9.59, and we gave them a $10 bill and we expected change back. Generally speaking, we expect to get the most precise or the most efficient coins back in cash. Imagine this. They owed you 41 cents. What would be your attitude when they gave you all pennies, 1 cent? They give you 41 pennies. How would you feel? Let's start out with that. How would you feel to get 41 pennies back? Instead of getting a quarter, 25 cents, 10 cents, and so forth. Too many pennies. Too many pennies. Okay. Now let me ask you this. Is it wrong, though, if I gave you all pennies? As long as it equals to 41 pennies. Matt, that's a nice way of putting it. You feel annoyed. You feel bad. So for some of us, it makes no sense. Why would they give me all pennies back unless, somebody gave them just pennies? Okay. So the way you feel is also not wrong. And I'm sorry, I'm going to use your last name. I don't want to butcher your first name. From Sani, he says, it is not wrong that they gave us all pennies. So just so that you understand it, we can break all of these. Like when we have the number 168, we could theoretically, I can give you whatever coin I want as long as it equals that number. But it wouldn't be the most efficient way of doing it. And we also have to do it within the restrictions or the constraints of what value of coins we have access to. So from a human perspective, unless they thoroughly dislike you and they just want to upset you, we would want to they would give us the cash back in a way that is the most efficient, and it would be the closest to what initially you're supposed to be owed. So that is why we start at looking, what is the largest value coin or just value that we can apply as we try to figure out the actual conversion. So in our case, we started off with 168. We said 128 is the first largest coin that we can use. And we turned this bit on by designating it with a 1, because this is what it says here. 1 equals on. We want to not ignore that. And we moved further down. Eventually, we got to 8. Now, at this point, we already agreed. We used 128 once. We did not use 64 because 64 would overshoot or would be too much to give us back just 40. So we decided to go with 32 because 32 would not be larger than 40. And then when we subtract these two values, we would be left with, oops, now I removed it. Let's do this. And then it would leave us with a remainder of 8. So that's how we got to this, right? We can't use 16. 16 is too large. And now the next coin that we have available, the next largest coin is 8. So would it now at this point make sense that if 8 is the next largest available value or coin that we can draw from, and we're still owed 8, that we would use this particular coin value, or in this case, it's going to be bit value. Again, we're talking about the largest remaining coin value that we have. Now we could say 4, and let's do that exercise. Let's say I don't want 8, I do 0. Let's say I want 4, it gives me 4. So 8 minus 4 leaves me with 4. Well, here's the problem now. You don't have any more 4s. Remember, you only have 0 or you have 1. You gave your 1 coin of value 4 away. You only have remaining 2 and 1. So at best, and if my math is correct, 2 plus 1 equals 3. So if I deduct 3, what am I left? 1. So guess what? You still owe me money. So does everybody see now why it would not work if we were just skipping values, but that we want to take a look at the largest available value when we're doing these conversions and use them first? Let me know in the chat if you agree with me. Because I wouldn't know what to do with this. You still owe me money with a 1. The computer doesn't know what to do with this anymore. Clear? That makes sense? Okay. Let's remove this. Okay. And just to finish it up, we did say we're going to use the 0. Correct. There are no 41 pennies. There was only one. Yep. There's going to be 0, 0, 0. So that's going to be the binary value of 168 will be read as 1, 0, 1, 0, 1, 0, 0, 0. Which helps us know that within each one of these decimal values, and since we have dots in them, we call them dotted decimal values, we're going to have 8 zeros, or a combination of 8 zeros and ones, just as you see here. Okay, so let me remove this. And let's copy the next one over. And the next value is going to be 1. Okay. Yeah, that's funny, Tara. My grandma operates on that, so she'd just give you all pennies. Is that the one you're talking about, Greg? Let me know if that's what you were referring to, Greg, before I move on. Want to make sure everybody understands how we got to this. Correct. Okay. Fantastic. Now we're going to go and work on the hardest one of all of them. We want to convert the decimal value of 1. So you all let me know, out of the values that we have available, what is the largest value I can use that would get me the closest to 1 in conversion? Would it be 128? And just so we have a little fun, if it's yes, type a 1. If it's no, type a 0. Get you guys speaking a little binary. 128, can I use it? Does 128 fit into 1? Again, yes, you type a 1, no, type a 0. All right, fantastic. Let's go with 0. Nice to see you guys are slowly speaking a little binary language here. Let's move on to the next value, which is going to be the 64. This is our next coin. 64, or 2 to the 6th power. Can I use 64? Does it get me to 1? Or does it overshoot? Or is it too large for the decimal value 1? And once again, let's go with that. If you think it is, so meaning a yes, no is 0. Fantastic. Let's go with a 0. Right. Let's go a little bit quicker. What about 32? Can I use the coin value 32? Let me know if it's a 1 or a 0. I know you know better, Kevin. All right, a 0. Let's speed it up a little bit. 16, 100. Let's pick up the pace. You guys tell me. 100 for 16. All right, Tarek says 0. Anyone else agree with him? Nada, nada, 0, 0. All right, 16 equals 0. What about the 8, the value 8? 0, 1. 0. Fantastic. And if you guys don't mind, it makes me feel good. I'm going to say we can't use the 4 either. That's going to be a 0. I cannot use the 2 as well. It is still too large. So I'm going to ignore it by placing a 0, or meaning off, and ignore it. And then finally, I get to our last coin, this beautiful, beautiful penny finally. So I'm pretty sure my math is going to be okay. If I take 1 and I subtract it from 1, I get 0. So I'm owed nothing anymore. So that means that I can add a 1. Does everybody agree with this? That the final binary value, the conversion for the decimal value 1, is 0, 0, 0, 0, 0, 0, 0, and finally a 1. I told you this was the hardest one. Throws you a little bit for a loop to begin with. Now, before we move on and we do the final conversion of the number 100, again, going back to what I said earlier, I want you to notice a pattern, specifically here. So I'm going to use a different color. We already said that we're doubling. As we move forward, we're always doubling as we move up in columns. I think everybody can agree on that, right? As you now look at the numbers though, and I want you to notice something important. Which one of the available values that we have here is not even? It's not an even number. Out of all of these that you have, which one is not an even number? All right, I'll give you guys a couple more seconds. Let's take a look. Ben says 1. Singh says 1 as well. Carol 1. Mike or Mikkel says 1. Victor 1. Dominic 0. I don't have a 0 here. I'm talking about these values, right? So 1 is not even. Okay. So let me ask you this. Since this is an interesting pattern, and it's the only odd number or uneven number is 1. If I have this value on, okay, so when I turn on the 1, can I ever have an even number? So you turn this bit on. As long as this bit is on, can I ever have an even number? Feel free to just type no or yes, and then we'll go through the exercise of something you can or you cannot. Okay? Prasad says no, Singh says no, Suran says no, Ben says no. It's always going to be odd from Suran. Yep. You guys are spot on. So again, noticing the pattern, a little tip. If you ever get a number, either from a conversion from decimal to binary, or you do the reverse conversion from binary to decimal, and that first bit, that 1, is on, and you get an even number, we did something wrong. So keep that in mind. So anytime you say anything that's uneven, that bit needs to be on as we go through the conversion. So in this case, this was the only value, right? When we look at this top out of this decimal value, 192, 168, 1.100, that is odd. So if we were now to convert the 100, which we'll do in a minute, and for some reason, this bit that has the value 1 is turned on, we did something wrong. Okay, so again, just put that on your cheat sheet if you have one, or on the side, just write that on. Anytime I have an odd number, this bit needs to be on. If it's off and you get an odd number, you did something wrong. If it's on and you get an even number, you did something wrong. So just keep that in mind. Okay, so let me remove this. And let's do a quick copy of this last. Let's move up a little bit. Right. And we said our last number that we're going to be converting is 100. Okay, so let's write that down. Let's delete it. All righty. So a question to you. What is the closest coin value that I can use to get to 100? Is it 128? Is it 64, 32, and so forth? What's the largest coin value I can use to get to 100 now? All right. So fair enough. We all agree. I can't use 128, but I can use 64, right? So just as we did with our previous exercise, let's see what is remaining. We're going to subtract 64 from 100. So 4 to 10 gives us 6. We carry the 1. So 1 plus 6 is 7. 7 to 10 leaves us with 3. We carry the 1, and eventually we have 0. All right. So everybody agrees? Fantastic. So let's move on to the next largest value we have available, which is going to be the value 32. Would that work when it comes to 36? Is that a value, a coin that we can give to a customer? Right? Carol says yes. Okoli, take a look again and let me know. Does 32 fit into 36? All right. Okay, we already used 64, so we can't use it. Next available coin we have is 32. Okay. No, it doesn't. All right, so let's do this. Let's verify. Let's show work. Let's go with 32. 6 minus 2 gives us 4. 3 minus 3 is 0. Okay, so 32 does fit into 36. So that means we don't want to ignore it. We want to pay attention. We'll add a 1. Okay, perfect, Akoli. Glad you got it, right? So next, we have a remainder of 4. Can we use 16? Does 16 fit into 4? What are we going to type here? A 0 or 1? Are we going to pay attention to the 16? Or are we going to ignore it? 0 means ignore. 1 means pay attention. No. All right. We're going to ignore it by adding a 0 then. Okay, fantastic, guys and gals. I'm going to use my math brain and confirm that we can't use 8 as well. We can't just, cram 8 into 4. So we're going to ignore this and add a 0. But now we're here. Our next available largest value or coin is 4. Rhetorical question. Can I use 4? Yes, I can. So again, we don't want to ignore it. We want to pay attention to it. We want to turn that bit value on by adding a 1. And then since we have nothing left over, we now have completed the conversion of 100. The remaining bits, which is 2 to the first power, or the decimal value 2 and 1, we're going to add to a 0. Does everybody agree with this so far? Great. Okay. So what you just have done in this little amount of time, and you should pat yourself on the back because you've done one of the hardest things when it comes to subnetting and get it started. And that's doing the conversion of decimal to binary. And you've done this, believe it or not, with 32 0 and 1s. And in fact, what you have now created is this number. You have created 1 1 0 0 0 0 0 0 dot. Okay, so that this was this. And let me make this a little bit bigger. Okay. Then we have our next value, 168, which is going to be represented as 1 0 1 0 1 0 0 0. Okay. Then our next value would be 1. The one that could be a little bit tricky in the very beginning. It might throw us off a little bit. But there we did the math, we verified it. We said it was 0 0 0, and then 0 0 0, and then finally the last bit, the one that designates if something is odd or even, in this case it's odd, is 1. And then finally, let me move this down a little further so we have some room. We get to our final number, which was 100. And here it was 0 1 1 0 and 0 1 0 0. And that translates into the human terms of 192, 168, 1, 100. Now we're going to do one final exercise before we go on to trying to figure out, since Mike mentioned it earlier in regards to having particular values or particular bits mean that they're part of the network, while perhaps other bits mean they're part of the host. So before we move on to that though, we're going to do conversion just to test. But take a look at this. This here, this 32 bits of zeros and ones, you guys just converted. You've done one of the hardest things when it comes to subnetting. So let me ask you this. You think you guys are going to be capable of converting binary into decimal? You guys want to see how that is done? Type a yes. All right. So let's do this. Let's go. Actually, I'll just write it down here. If you remember, we said 0 equals off, and we said 1 equals on. And we also said ignore, and then we said pay attention, right? We'll just do it like this, pay attention. So I'm going to ask you as future engineers, as future architects, cloud enterprise, and so forth architects, we now know how to convert decimal, how we take 100 and we convert it into these binary bits. How do you think we go back, or the opposite direction, from just this value to understand how we get to this value? What do you guys think? We'll walk it through it together.
Mark, let's pause for about 30 seconds.
Sure.
Come back on screen, make sure everybody's good. You covered a lot of really great information, Mark. So thinking about this, everyone, you know, I want to make sure that you all understand it. So not only are we going to finish the webinar, I love the job Mark's doing. He's explaining it. We're going to open up, say, a 30-minute Zoom session after this webinar is over. And you can ask me, and you can ask Mark questions. You'll get to hang out with Alonzo, get to see a lot of our leadership team. Chris will be behind the scenes because he's finalizing our AI architect program, which comes out tomorrow. But if you want, I'll give you 30, 45 minutes. We'll get on Zoom after this. And that way, if there's any questions or areas of clarification, my team can give it to you. It's going to be free. I just want to help you all. You guys all happy about that? If you want a Zoom session, pop Zoom session in the chat box. Because I just want to know that everybody understands it. While you're at it, if you're looking to become a cloud architect, we've got a free guidebook for you. Download it. It's free. We really want to assist the best for you as much as we can. So perfect. I'm watching Mark. I love the way Mark's doing this because, the way I learned it, it was like it was taught by like little robots speaking different languages that weren't Greek or English. So it was a little challenging the first time, and I had to figure out my own way. So, Mark, keep it up.
And fair warning to everybody, I'm going at snail pace right now for a reason. Once we get into the subnetting, I'll give you maybe 3-4 examples max, and then we're going to take up the tempo because I'm going to expect you guys to be pretty good at this. Just fair warning. That's why I'm going at this ridiculously slow pace. Okay? So let's do...
Turtle is good. Slow is smooth. Smooth is fast. We'll get there. So
slow and steady wins the race.
Mark's going to get back to what he's doing. At the end of this, we're going to jump on Zoom. We'll give you the opportunity and a link to do so. We're going to do that because you're limited to the questions you can ask in a chat box. But live on Zoom, we can have a face-to-face conversation, have a virtual cocktail, if you will, or apple juice or whatever it is, whatever the case is. So I'll let Mark go back to what he's doing. He's doing a great job. And then we'll give you a little bit of a bonus session live on Zoom where we can talk right after.
I'm about to pop a link in the chat box right now. Thanks for keeping me on my toes, Mike.
Hey, Mark, I'll turn it back over to you.
All right, thank you. And then, all right, Chris already shared it. So we'll take a look at this. So we mentioned that 0 means off, ignore. We said 1 means on, and pay attention. So when I'm looking at the conversion that we already have done here, and I'm horrible at drawing straight, apparently, how would you imagine that we do the conversion here? And just give me 1 second. All right. So let's walk through this together. We're not going to divide, right? Again, I'm showing you how ridiculously easy and simple this is. We're not doing any division. This is mostly addition and subtraction and pattern recognition, something we're humans are pretty stinking good at. So let's look at this. So we said that 0 means ignore, right? So we're looking at the first value here. 0 is ignore. So we don't care about it, right? Let's get rid of it. We don't care about it. That one is done. I'm looking at the next value, which is 64, and it's on. So I want to pay attention to that. So let's do this. Let's write down 64 here. Okay? Next, I'm looking at 32. 32 is turned on, right? Because we see the 1. So I want to pay attention to it. So I'm going to write it down here. Then I'm looking at 16. Well, 16 is turned off. We know this because of the 0. So what I'm going to do is I'm just going to ignore it. There's no point in paying attention to it. I'm just going to ignore it. I'm going to do the same with the 8 because it's set to 0. But the 4 is different. The 4 is turned on. I want to pay attention to it. So what I'll do is I'll write it on the side here because I don't want to forget about it. Okay. I'm going to look at the 2. The 2 is set to 0, which means I'm going to ignore it. And the same is for the 1. I'm going to ignore it. So now, as I mentioned, it simply is addition. I want to figure out what the total sum of the values is that I want to pay attention to. So this would mean I'm going to add 64, 32, and 4. And since I know my math was correct before, because you guys confirmed it for me, I know that equals 100. Does everybody see how we just did that? We converted from binary back into decimal. And how we did that? By using the decimal values that we turned on with a 1. Does that part make sense? Carol, glad that it makes sense to you. And that's all there is to it, to converting from binary back into decimal. And we'll do one quick example here, just one quick additional example, just so you guys see it. Okay, let's go to 1. And I'll run through this quickly because I can do this one. I'm going to ignore the 128. I'm going to ignore the 64. I'm going to ignore the 32, the 16, the 8, the 4, the 2. Why? Because I'm being told to ignore them by the binary value of 0. But 1 is turned on. So if it's just 1, guess what? My binary value being ticked on at 1 is a decimal value of 1. You guys want to let me know if that's correct? All right, fantastic. Let's go to 168. I see that 128 is ticked on. Let's make sure we write it down. So that'd be 128. 64 is turned off. I'm going to ignore it. 32, I see a 1. So I want to write that down. 32. 16 is turned off. I'm going to ignore it. 8 is on, right? So I want to write that down. 4 told me to be ignored. 2, I'm ignoring because of the 0, and as well as 1. So now all I have to do is add these values up, which 8 plus 2 gives me 10, plus 8 gives me 18. 1 plus 3 is 4, and 4 plus 2 is 6. And then we add the 1, and we got the decimal value of 168. Right? And then that's correct, Okoli. So when it comes to looking at which binary values we want to pay attention to and how they translate into our decimal weights, because these are our decimal weights, right? The decimal values we have assigned to each of these different positions. We only pay attention to the ones that are turned on. And turning them on is designated by placing a 1 on them. Now, it's done a little bit different on the wire. That's done through voltage or through light if we're using fiber. But for all intents and purposes for us, we use just the binary value, the actual computer language that networks and pretty much anything else use of 0 and 1 to designate which values we're going to pay attention. And then the decimal is just something that we understand. Because if you look at this, this is not very friendly for us humans to read. Now I added the dots, so at least separates the 0s and 1s. But if in reality for a computer, this is just one large string. There are no breaks in between it. The computer sees this as 1 1 0 0 0 0 0 0 1 0 1 0 1 1. So that means nothing to us. So that's why we're going through this conversion. And then of course, we'll just finish up to make sure that we're correct. We're going to go up here. We're going to ignore this 32, the 16, the 8, the 4, the 2, and the 1. We're interested in the 128 and the 64. 4 plus 8 is 12. We carry the 1. 1 plus 6 is 7. 7 plus 2 is 9. And 1 and 192. So let me know in the chat, is it really that difficult to work in binary, convert from binary to decimal, from decimal to binary? Or you guys feel pretty comfortable with this, you guys and gals? No, right? So, and what you just saw us do, this is what we're going to do predominantly. The only thing that we're going to start doing is we're going to start to figure out now the range of our networks. What is the beginning? What is the end? What is that creamy, gooey filling in the middle of it? That's what we're going to eventually focus on in subnetting, how we can take those numbers and add to our benefit on being to either divide them or aggregate them, which means place them together to get a larger network. We call that aggregation or supernetting. While subnetting means we take a larger something, if you want to think of it like a pie or like a pizza, like Mike said, and we divide it up so that we can give pieces to everybody so everybody can share in that type of meal. So yeah, and we'll get to it, Draw with AI. You're going to be fine. You're going to enjoy this. So Mike, if you're still around, and Chris, if you want to bring me back up on the screen.
I am absolutely around. I think Chris may be back in a moment.
All right. There he is.
He's here.
Yep, looks like he is. At least he got punted back. So did we want to continue on YouTube or?
No, we're going to finish the session on YouTube.
Okay.
And then after YouTube, we're going to go to Zoom for anybody that's got any questions.
Got it. All righty. You okay if I start talking a little bit about how we actually figure out the network and the host portion?
Absolutely, Mark.
All right. Chris, if you don't mind, go ahead and share my screen again. All right. So let's do this. Let's get rid of, well, not that. I just want to get rid of this. Oops, it's not going to let me. All right. Let me remove that. And here. Now, a next logical question would be, because we're talking about addresses. So we said this was the 192, the 168. We said this was 1, and this was 100. So this would be a IPv4 address. One would be written in decimal format or dotted decimal, while the other one would be in binary. Now, when I learned subnetting, the next logical question I had is, how do I know which portion belongs to the network, equaling, I'm going to say, routing, or you might even say the building, if you want an analogy, and which belongs to the hosts? And this will be people, if you want to look at it that way. And for IT purposes, we would call these servers. We would call them PCs, IoT devices, whatever they may be. So that was my question. Do you guys want to take a guess in the chat? What would be a way that possibly we might be able to figure this part out? I give you a hint. If you look at what we did previously, we used the ones and the zeros to help us figure out what numbers we want to pay attention to and which numbers we want to ignore. So that what they figured out was we moved from a concept where all we had was a classful range of addresses, meaning they had what they call the class A, like Mike showed, a class B, and a class C, and a few more. And they said within these, we would turn on certain bits that would tell us that we have, let's say, an A from 1 to 127. That will be the decimal value, for example. And then it will move on, let's say 1 to 192, and then 192, and it finishes off, right? Whatever this is. So this is designated an actual binary. So what the computer used to do, it would look at its address. And again, you don't have to do this anymore today, but it's the foundation stone so that you understand why we're using what we call a subnet mask, or how we denote what is called a prefix length. Okay? So what the computer initially would have done, it would have looked at the higher order bits, meaning the first bits. And if they were turned on, it would know if it belonged either to a A network, a B network, or a C network. And then you would have the ranges, whichever were part of the networks. If it was A, it might be 1 through 127 and so forth. And then it would know to say, if that is the case, so let me remove this. If that is the case, I want to not ignore this, but I want to pay attention to it. And it went through the same process. What it would do, it would add ones as a check, remember on and off, in the octet, and octet being, again, the position, in which position we're in, and the first, second, third, and fourth. It would set it all to 1. And if that is what the network, or the actual part makes up the network, it adds the 1, and on the rest, it would add the zeros. And then let's say this is all zeros here too. Actually, I'll draw it out. Let's do this. And then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay? So far, so good. We're using, again, we just have 2 values, zeros and ones. Ones, we want to pay attention to it. 0, we want to ignore it. So this is initially how they did it, and it was added to it. And then, as somebody mentioned, and Mike mentioned this too, we moved away from this classful concept, and we went to classless interdomain routing, which meant that we can now use all the ranges and sizes in a hierarchical order. So you think about like steps of what we have available. But now the challenge was the computer wasn't going to look just at the first higher order bits anymore. Meaning it wasn't just going to pay attention to the first few bits and try to figure out if it was part of an A or B or C. So now what we needed to do, and this is where the concept of a subnet mask or prefix length came in, and we needed to extend how far across we would add ones to check and allow a computer to understand what makes up the network portion. So in this case, and I'm going to show you guys how this works now. And this is going to be one of the few times that we do it by hand, because this is going to get cumbersome. But let's say we go with a /24. Okay, and this is how it's written. This is what they call a CIDR notation. Or better yet, especially as we move on to the BGP workshop next week, when you see this type of delineation or denotion, what you want to call it is a prefix length, meaning the network portion, what we've displayed. And let me show you from the slides here. Everybody can see that. So we see this length of different networks here. We had we see this would have been my A, this would have been my B, this would have been my C, right? There's bits in here, basically 0, 1, zeros, and so forth. That would have been involved. It says that anything to the network is going to be all ones. Anything in the host would be all zeros. Okay, that's how I would figure it out. So that's how initially it was. We had to figure out a way, how would we now delineate or figure out what it would be. So what we're going to do we're going to turn on 24 bits in our example, okay? Since we have the slides, I don't want to keep it. Let's go back to this. And that's what this represents, 24. So again, we need to do a check on what belongs to the network. So we're going to add ones, but we're going to add them from left to right. That's where we're going to add them. So this is going to look something like this. We're going to add 24 ones. So it's 1, 2, 3, 4. 1, 2, 3, 4, which gives me 8. And I hope you guys don't mind. I'm just going to copy this. Oops. And if my math is correct, these are 8 ones, another 8, which gives me 16. And then 17, 18, 19, 20, 21, 22, 23, 24. Okay, and then the rest is going to be zeros. All right. So is everybody with me so far when it comes to this part, what I just did? So this is my IP address in binary. And through the consecutive ones from left to right, I'm setting up which bits I want to pay attention to, and I'm going to make up the network portion, my routing portion. So eventually that goes on a router, on a firewall, and so forth. My mask, yeah. So in this case, if you want to think of it this way, instead of obfuscating, instead of hiding, the mask hiding something, what we're looking to do is here have the mask reveal something to us. In this case, reveal to us what the network portion is. So the way this was done is, again, you go with 1. What does 1 tell us? Don't ignore it. They came up with this idea. They called it a Boolean AND, or I like just to call it the truth table. And the way this looked was very simple. You had values of 0 and 1, because that's all we had. And you would basically see if it's true. So in this case, the only value that would ever be true is 1 equals 1. Because 0 is ignored, so it doesn't help us. So 0, 0 would be 0, 0, 0, 1 is 0, and 1, 1 is 1. So now you don't need to remember this, of course, if you've taken a test or anything, but this is actually what the computer, the router, the firewalls, they all do. They take these ones and they compare them. If it's a 1, Boolean AND logic, correct. If it's a 1, I'm going to keep the value in place. And then eventually we add decimal values. Okay, so the way that would look, I'm going to use a pen here, is this is 1, so I keep it in place. It's going to be 1. This is another 1. This is 1. The top value is 0. This is 1, which means it's now a 0. This is a 0 again. And as you take a look, I'm going to speed up. These are all zeros, which means this is also going to be zeros. You guys see how I did that? So anytime I have matching ones, I leave the bit on. And when I don't have matching ones, such in this case here, I turn the bit off. Let me know in the chat if you follow this so far. Okay, Anna, thank you for letting me know. Anyone else? Does this make sense so far before we move on? Okay, let's move into the second octet. So basically this octet. And let's do the same. We start off with 1 compared to 1 equals 1. 0 compared to 1 equals 0. 1 compared to 1 equals 1. 0 compared to 1 is 0. Again, we're basing it off this truth table. 1 compared to 1 equals 1. And then we have 3 zeros compared to 1s, which will equal 0. And now I'm gonna just go through this because to speed up time a little bit, but take a look here. We have 0, 1 is going to be 0. It looks like we have a consecutive string of zeros compared to ones. So we're going to set these all to zeros. It looks like we have 3 more zeros. And then finally, at the end, we have a 1. So we'll add this here. And the remaining value is all zero compared to zeros. So guess what? We set these all to zeros. And now what you would have to do is you would have to take the binary value that you have here and convert it into decimal. And that would be your network ID or your network address. And the only way to figure that out now was because of the subnet mask and how it does the Boolean logic, the truth table, and checking to see which bits are on and if 1 equals 1 and turning them on. So in this case, and you'll notice now something interesting. If we do the conversion, it's going to be very simple. Is I have 2 1s on here, I got 2 1s on. So you'll notice this equals, again, 192. I look at 168, and oddly enough, I got 1010, 1010, 1000, and the same down here. So this equals 168. Next, I'm going to look at the third octet, the third position of interest. And here I'm going to see that every bit is set to 0 except the last one, which would equal 1. And in the end, everything is set to a 0, and it's 0. So this way now, the computer, the router, the firewall, load balancer, everybody knows which network they belong to because of this Boolean logic that it checked, the ending, that's correct. And if we want to just do a quick conversion, we said this was the CIDR notation or the prefix length, the way we write it abbreviated. If we were to do an actual dotted decimal calculation of what the subnet mask, the one that reveals to us what the network portion is and what the host portion is, how it is written in binary, it will look like this. So again, take a look. We have all the ones turned on. And if we pay attention to our bit values here, 128, 64, 32, and so forth, if I turn them all on, does somebody want to type in the chat what value we will get if we add 128 to 64 to 32 to 16 to 8 to 4 to 2 and 1? What is it that you get when you add up all those values? So we're turning them on. All right, 255. Perfect. Now that's the first octet. What about the second one where we turned on all the ones? What would that be again? 255. Perfect. What about the third octet where we have all the ones turned on? That's correct, 255. And what about the third octet? All the values are set to 0, meaning we're going to ignore them all. What would that be? The final fourth octet. Nothing is turned on, right? See, everything is turned off. 0. So now that you see this, and you might have seen it in documentation, maybe on your own computers, does it make sense how the value for the subnet mask in dotted decimal notation is derived? So basically, as we turn these bits on, you add the bits to each other. And that's how you start seeing the different values, right? So if we go back to originally, what you saw me have. Let's say we go to this example. Okay. I'm going to wait just for the screen to shift here. Okay. So this is not an example where I originally had this column and row set up, where as we turn on each of these bits, in this case, only this bit was turned on, 1. So that would equal what? 128, right? Because that's the value of this bit position. Then I want to turn on the next one, which means now I have to take 128, and add 64 to it, and I get 192. Then I want to turn on the next bit. And if you notice, we're doing nothing different than what we did before. We're just paying attention. We're not ignoring the ones. Whatever is a 1, we're adding to each other. So now I have 3 bits on. So now I need to add 192 to 32, and I get 124. I'm going to continue. I want to turn on the next bit, which is, let me do this here, which is 16. So I'm going to take 224 and add 16, and I'm going to get 240. And that I'm going to continue onwards from left, so basically from left to right. And as I turn them on, all I'm doing is adding the values together. And then eventually, as we said, all ones would equal to what? 255. If I did not turn on, let's say, this last bit, but I still added all the previous values together, I would have what? 254. So does everybody understand what the subnet mask is for? Meaning we want to figure out what belongs to the network for routing purposes, and also so that we can size and understand what the beginning and the end of our network is, and how we derive the values that we see, such as a /24, and even these different dotted decimal values, 128, 192, and so forth. And Chris, maybe if you can bring me back up on the screen as well, and Mike, and see if we need to take any questions. And I know Mike probably hasn't seen this in a while. It's generally taught in CCIE books when it comes to the Boolean AND logic. You don't generally see this in CCNA books and so forth. So, but I wanted to show you again, how does a computer figure out what it is? Because as we go forward, you don't want to be doing this in your head. I mean, I can't do this in my head. I have to write it down. That's the whole purpose. So what do you guys think? So Advent says it's a little bit confusing. Carol says, how do we end up with 0 at the end instead of 100? Where was that at, Carol? Remind me, so I can go back and take a look at it.
So, well, we wait for Carol. That's one of the reasons we're going to go on Zoom after this. I mean, we're going to finish the session, but afterwards, if there's a point of contention or clarification, we'll jump on Zoom, because it's a little bit of a struggle to get the information in the chat box. But we're going to try and see if, Carol, if we can get your information cleared up right now anyway. Let's see if which one.
And what we'll do is, I'll wait for Carol, see what she says. What we'll do is we'll jump into doing some calculations on networks. And we're going to be seeing if we can, through the binary math and the decimal math, if we can figure out certain values. And then we're quickly going to tackle as well as, what if I gave you a requirement, such as create me a network that needs 500 subnets? How would you go about doing that? From whom do I need to take something to create something else? Because I can't create something from nothing, right? So let's see.
It looks like the question is related to the binary conversion after turning all values on. The good news is, I think what you can do is I was going to say that'll bring us back to the decimal conversion.
Yeah, so I tell you what, Carol, let's do this. Let us go through several examples because we're going to continue on with the conversions and turning on the bits and adding them so that we can figure out what the value is. If you're still confused about that, let's get on Zoom a little bit later on. Let's hash it out. Maybe you and I will do a quick one-on-one session just to kind of go through another example. And maybe that will make it a little bit clearer to you as regards to what happens when we turn something on by designating it with a 1, and what happens when we turn it off with a 0, the ignore bit, so to say. Okay?
And Prab, we're definitely going to do those exercises you're talking about. They're coming up.
I tell you what, let's go ahead and do that. Chris, if you don't mind sharing my screen again, let's do them together. And we're going to have some requirements that we're going to have to look at. Okay, so let's see. First of all, is this big enough for everybody? Clear enough for everyone? Just let me know in the chat if it's yes or no. And I'm going to explain a little bit what I did here, just so that we have a reference point. We generally call this like our little cheat sheet when it comes to subnetting, where we have the subnet values, which are derived by us turning on the bits and then adding them just like we did before when we did the actual binary to decimal conversion. That's what this top part is. And then what you all already have been familiar with and you've written down on your own piece of paper is the actual decimal value per column, right? So 1 would equal 2 to the 0 power, 2 equals 2 to the first power, and so forth. Now, what you haven't seen before is this prefix length field here I've added, or the classless interdomain routing number, right? We call this CIDR. I don't generally refer to it as CIDR, I just call it prefix length, because once you get into routing, it makes a lot more sense, and it's easier to continually talk instead of saying CIDR or CIDR. But anyway, so this is the table that we're going to be using to figure out what our network ID is. So this is going to be what makes up our network portion. Then what we want to figure out is what is our valid IP addresses. So those are going to be the addresses that we can assign to servers, to PCs, or any type of other hosts or end stations. Our local broadcast IP, that is a particular and special IP address that's going to be derived out of the larger range. And generally speaking, there's certain application storage, such as in a multi-access network, such as Ethernet, where the assumption is made that everybody is in the same room and they all need to be able to shout at each other. That's one way to doing it, trying to find somebody, so neighbor discovery. And then another way that the local broadcast, so broadcast, think about it, shouting it out to everybody that they can hear, is when we have a, let's say, a component such as a server that can hand out or assign IPs or IP addresses dynamically to those people that ask for it. And it uses a protocol such as the dynamic host configuration protocol. So this is very important also to understand how we get it and how it is derived through the math. Then eventually, we also have the prefix length, or as I've written down here, is the subnet mask. So we want to figure out as well, what is that value? How do we derive it? And then just to help you guys out a little bit so that we can keep organized and keep track, is we're going to look at what would be the next network, the one that might not belong to me, my increment. I'm going to explain a little bit what that means exactly. And then finally, and this is the real piece that helps us stay organized, what interesting octet, meaning where in this IP address we're going to be interested in performing our calculations. So yes, let's see, 25, 26, 27, 28, 29, 30, 31, and here. Yep, thank you for catching that, and I'll correct it also on the other slides. So the number that we're starting off with here to do our calculation, again, now we're trying to figure out, somebody subnetted this network. We were given this. we were given a /8. We'll have to figure out what this /8 means and how it can help us to figure out the rest of our range, but it is right there. So we want to figure out, by using this chart, all these different values. So the way that we're going to be initially approaching that is just what we showed earlier, was to figure out what is my subnet mask, because my subnet mask is going to tell me how far my network reaches or is made or makes up this number. So that means we need to figure out what this 8 means. So I'm going to write it down and show you guys. So this means 8 bits. So each one of these positions has a total of 8 bits. So if you want to think about it, this would be 8. Then this has another 8. Here would be 16 total if we add 8 plus 8. Then the third octet would have an additional 8 bits. That would give us 24 total bits. And if we used all these bits up, and right now we're not discussing if it's for subnet or if it's going to be for host, but just in general, we would have 32 bits. So we would have a combination of 32 zeros and ones. And that is the actual size also of what we have available when it comes to IPv4 addresses. Okay? So what this 8 denotes to me is that our subnet masks or our prefix length is 8 bits long. So how would we write that? If you remember, subnet mask is written from left to right and is made up of a consecutive strings of ones. So if I have 8 ones, it will look something like this, right? So let me write here, it will be 1, 2, 3, 4, 5, 6, 7, 8. And that would be my first octet, right? From left to right. And then we have this number 10. We'll add this to it, just so that we know what our decimal value is. And then the remaining, so in this case, the remaining 24 bits that we have available will be zeros. So I'm going to add them in here. This, in essence, will be the decimal number 20. We're not doing a conversion yet. We're just showing the subnet mask. Then we would have more zeros. And this will correspond to this octet, which is our third, which we originally had the value of 115 in it. And next, because we only have 8 bits that are part of the subnet mask or the prefix length, we're just going to write it out. And in this case, we said we had the number 100. Okay, so in binary, once again, this is how our subnet mask looks like. If we now went back and we tried to figure out what would this look like in decimal, because we want to write it in here, what would it look like? What we just did is we turned on every one of these bits. We turned them all on. As a matter of fact, I'm going to do this so that we can see it. So, as a matter of fact, what I did this. Okay, in the first octet, right? So I'm only looking at this first position. I turned them all on. And as we did before, what we would do is we would now go ahead and we would add all these values together, because by placing a 1, we said we want to pay attention to it. So does somebody want to type in the chat what would be the decimal value that we would derive from then in the first octet? If we're turning on all the ones, and now we need to add 128 to 64 and then so forth. And you can cheat if you just look here at the top. All right, 225, perfect. 225, got it. And then I'm gonna make it easy. The remaining bits in the subnet mask, the prefix length, is turned off. with a 0. So naturally speaking, the remaining 24 bits, and we're going to write this in decimal, we can simply write them as a 0, as a 0, and as a 0. And that's how we come up with the prefix length or the subnet mask, and we're doing the conversion. And the reason I'm showing you this, you might be on a test, or you might be somewhere where they're going to be quizzing you, and you might not get a prefix length or this CIDR notation like a /8 or /12 or /18. They might just give you a decimal notation that you have to figure out what the 250, what it actually is. Now, Tarek, the 10.20.115.100 is the dotted decimal format for the IP address. So meaning an address that I can assign to an actual server, a host, a firewall on my network. So that's what that is for. I just wanted to show you so that you can visually get an idea that in what position we're working on, right? Originally in the first position, we have the number 10. We turned the subnet mask on in all consecutive ones. We left them off everywhere else because we only have 8 bits that are supposed to be part of the prefix length. So those are we turning off, but these values are still part of my IP address. And we're going to look at how we're going to figure out the rest of the things now. Okay. So does it make sense so far for everybody how we derive the subnet mask and how we convert it from binary into dotted decimal and how we interpret the prefix length, the shorthand notation or CIDR notation as some call it. So all this means is how many ones make up the mask that is going to reveal to us what the network portion is. Okay. So before we move on to trying to figure out some of the valid range and so forth, if I know what my subnet mask is, I know that it's a consecutive ones, right? So I would normally take my 10 and I would convert it into binary. And then you and I, we would generally go through the whole process of the Boolean AND logic. One, is a 1 equaling a 1, yes or no? We're not going to do that because all we need to know how many of the bits are on in the mask, and that will tell us what our network or what bits are part of the network. So in this case, we only have 8, which means that the only decimal value that's going to be part of our network ID is going to be 10. That's it. The remaining 24 bits are going to be hosts. Right? So I'm just going to write that as host right now, which means Suran, we don't deal with classful addresses anymore. We're dealing with classless. So you might hear us still talk about A and B and C address, but for all intensive purposes, these are just going to be now /8s, /24s, /16, whatever the amount of bits are going to be active in the mask, that's all we're going to refer to. The concepts of using class A, B, and C, that's legacy, that's old, that's outdated. That was more to show you that there was some hierarchy built into it as we open up the rest of the network range. Okay, so this is actually referred to classless interdomain routing or CIDR. And if you guys like, I'm going to pop it in the chat. I'm not trying to overwhelm you guys, but this is the actual, let me see.
I popped it in the chat for you, the CIDR, Mark.
Oh, okay.
About a minute ago.
So that's the actual RFC for you guys. The request for comments that outlines what CIDR is, why it was brought about, and why do we use it. And this particular document, so that everybody understands, subnetting always existed, supernetting always existed. But there was problems with exhaustion of IPv4 addresses. There was a problem with the routing table for the internet growing too quickly. So what happened is they needed to update the allocation method, the way they were handing out IP addresses to organizations. And that's how we eventually got to the standard of CIDR, classless inter-domain routing. And it's written in shorthand just by how many bits are turned on, just like we did here, that make up the actual network address. But the reason we do the conversion to dotted decimal is that, let's say you go on a test, you might see both versions or formats, /8 or at 2255 and so forth. So you'll have to understand how to go and convert between them, what they mean. If you're actually doing, let's say you end up being an engineer or you get on a simulation or some type of lab, let's say you take the CCNA exam, the actual version of code that they give you in the routers, they're not going to accept the shorthand notation. They're going to want you to know how to type this in, how to tell it in dotted decimal, how many ones are actually part of the network portion of the IP address. So that's why we're doing both. And to be honest with you guys, go ahead, please.
That link that Mark gave you guys is actually to the specification. I'm going to drop the other link to the main site. If you want to know the specification of anything in networking, OSPF, BGP, private addresses, subnetting, classless interdomain routing, it's all going to be completely free at that ietf.org website. So I dropped that for you in the website because when I saw Mark put it there, I thought we might as well give you more.
Yeah. Now, I'm not expecting everybody to read through it, like from cover to cover, but if you feel like it and you actually want to see why we're using it that way, you're welcome to read that document and get it straight from the horse's mouth, as they say. All right. So that's the subnet mask, so that we know that only the first octet is part of the subnet mask. So in that case, that means my network address, the one that's going to be part of my routing, is going to start with 10. Because I want 8 bits from left to right to be recognized, 10. Now, since we're ignoring pretty much the rest of the 24 bits, my network address is going to look like this. And then we can add the /8 to it as well, just so that it makes sense. And that's simply because of this. We only care when it comes to the network portion this way. So that means this is the beginning of our network, 10.0.0.0/8, meaning how many ones are present. Now the question comes, how do I figure out where I need to actually do the math to figure out what is my valid IP range? What is my local broadcast? How do I know where the next network begins? And then as well, what is this increment and why do I care about it? So I'm going to start first with the interesting octet. That's where I'm going to start off, and I tell you why. I first need to know where do I perform my calculation. So in this case, I'm looking to figure out what is my range. Well, if the first 8 bits are taken up by the network, can I use, the way it is right now with 8 bits, any bits from the hosts to calculate anything further with the network? Is that permitted based on this prefix length? What do you think? Just to figure out this information. We're not talking about subnetting it further. No. Okay. So my interesting octet, the position is going to be the first position. So we want to write that down, basically this one, because that's going to be making up the network. Next, I want to figure out my increment. Basically, by how much does my network grow? And how does it define my boundaries beginning to end? That's what this is. Some call it an increment, like myself. Others call it the magic number. The way this is derived is actually quite simple. What you do is you look at your ones. And what you do is from left to right, you follow them until they stop. So in this case, they stop right here. which means this is my boundary between my network and my hosts, or my subnet, whichever it may be. And then what I want to do is I want to look at the first number to the left. So in our case, it would be this one, or this particular value. So now I want to know what is the decimal value of this bit position. And that's where this table comes in. So you guys tell me, what is the value associated with this bit position? Okay, James says 1. Does anyone agree with James or disagree? Well, remember, this is the subnet mask value. I'm asking about what is the bit value. I was just pointing here so you know what column I'm talking about. I'm looking at these values because we're trying to figure out what this 1 means in decimal. Okay, it's actually going to be 1. So let me show you guys how we would do this. So I'm going to take this table in regard. So from right to left, my first position is 1. And let me zoom in a little bit so that you guys can see it. Okay, so my first position is 1. And remember, binary, we're doing multiplications by 2. My next one is 2. Then I'm going to 4, 8, 16, 32, 64, and then finally 128. So as you can see, this is nothing new. All I did is I wrote down the decimal value of these binary positions. That's all I did. So if I was to remove all of them, and we're simply now focusing on this one, what is my decimal value for this bit? Is 1. That's right. So my increment for my network is going to be 1. And I'm going to write that in there. Okay? So now there's going to be shorthand ways or quick ways of doing tips and tricks. We're not going to get into that. We'll do it on the next example. But quickly, what I wanted to show you guys here is that we know by what size my network increments when it comes to these numbers, which is the 1. Okay, so I'm going to leave that there for a second. I'm going to move on though before we do this, because this is going to be more like a quick way of doing it once we know this value. And I want to focus on the beginning and the end of our network. Some refer to a group size as well. Everybody has a bit different verbiage that they like to use it. I learned it as an increment value, by which amount I increment my network space. Some may have learned it as a magic number. I'm not sure what Mike learned it as. Maybe he can chime in and let us know what verbiage they back in the day taught that this increment value would be. But yeah, it could be also group size.
I wish they gave me something simple for that, but when I started in networking, it was kind of the wild, wild west.
They probably just gave you the truth table and goes like, here you go, figure it out.
That's exactly what they did. They said, here, it's a 32-bit address. It's either 0 or 1. Go figure it out.
That's correct. Yep. So at least this way we're breaking it down. So let's take a look at this way. So I'm going to remove these just quickly, the hosts. I'm just going to remove this. We do know the following, that this is our network. These are going to be our hosts going forward. So if I wanted to know what the first IP address would be in my network, just logically speaking, how do you think you would do this? And now you're going to have to think back to the very beginning when we added values. how we incremented these values, and then eventually how we also incremented positions or added positions or columns. So we generally did what? We went to our last value, our last position. And if I turn this on, meaning that would denote my first IP address. So this is I'm going to write the second octet, third octet, and then this is my fourth octet. And what I mean with that this is the position values here, right? And what position we're in. So right now, we're strictly looking at this position because that's how I turned on, or where I turned on my bit. So if I turn on the last bit, and again, looking at here, what is the last bit? Or in this case, it would be the first bit, this one. That would be a 1. Okay, so what I would have to do then is do simple conversions. If this is a 1, the decimal value is 1. The rest is still set to a 0. So how would the first IP address look like? Would be 10, because I can't change this. This is part of the network. I haven't changed the second or the third octet, so those remain zeros. But I did turn on one bit, and that bit has the value of 1. So my first IP address would be 10.0.0.1. Does everybody agree with that and understand how I got that value? Okay, so that would be the first one. So the next thing I want to figure out, what is the beginning and the end? Well, the beginning is this, right? This is the beginning, sorry. This is my first IP address. So I want to now figure out what is the end of my network, or the far right. That is correct, Danka. I'm changing now the actual host portion because we're trying to figure out what IP addresses can I assign to hosts. I can't change the network portion here. We're not doing any actual division or subnetting of this network. I'm just helping you guys understand how this network is constructed based on the prefix length, the subnet mask, as well as the prefix, which is going to be the network portion that we call it. So if I wanted to now find out what my last IP address is, it's actually going to be very, very simple. I would take all of these host bits, so all of them, across all the remaining octets, and I will turn them on. So all of these are going to be 1s. All right. So Mick already wrote it in it. He told me what the conversion is, right? If we add all of these together, I will get 255. And you can also cheat a little bit and look on top, right? Because we see what happens when we turn them all on. This would be 255 and 255. Now, I see some of you just writing 10.255.255. But this is actually how this is calculated. So I can't change the first bit or the first octet. So what I would have to do is, looking at the second octet, I would actually add 255 to 0. Then from the third octet, I would look in here and I would see what my value is, which is 0, and I would add 255. And then the same thing for the last one, I would add 255 to 0. Does everybody see how I did that? That we're adding them to our beginning and to the actual octet in which this value was calculated. Same thing you've been doing this whole time, where you're just adding the bits that are turned on based on the bit value, those decimal values. So, yes, okay. So this is my beginning, and my end, and the last IP address, which means always the ending of a network, belongs to what we call the local broadcast IP. So that's going to be that IP address where everybody can speak to everyone. We can use it for protocols such as the dynamic host configuration protocol. So that is going to be a reserved IP address. So that's going to look like this: 255.255.255. Okay, so we have basically created two reserved addresses: the 10.0.0.0, which makes up our network portion that is used for routing purposes, and we reserve the final IP address, which is the 10.255.255.255, as our broadcast IP address. Our first valid IP address to use was 10.0.0.1. Now, you could do this. If I wanted to find out the last usable, meaning the last valid IP address that I can use, there's a really quick way of doing it. And that's simply looking at the local broadcast IP address, looking at what the last octet is, and subtracting 1. That's all you would have to do. But for this demonstration, you still will need to know how this actually works. So let's do this. Right. I want to know what the last one is. So I'm just going to put 000 back here. Now, I know if I turn on all the bits, I get basically the local broadcast address. So all I want to do is I want to turn every bit on except the last bit, because that belongs or would calculate this out to be the broadcast IP address. And then I go back. I simply take the bits that are on, I add them, which you can, again, if you take a look at this table here, you see what your actual values are, and this would be 254. And you will go through the same process again. You will look at 255, add it to the second octet, because that's where it was calculated. You do the same thing with the third one, and that's where you get your actual 255s. So that will look something like this: 10.255.255. And then we said the actual value of the last octet was 254. Let's make this a little bit bigger. Okay. So does that make sense so far, how we calculated the network ID, the first valid usable IP address, and the last usable IP address, the .254? Yes, okay, fantastic. So everybody else get it too? We're gonna do a few more examples, but we're gonna start speeding it up a little bit. So I just want to make sure everybody understood how we got to this. Hopefully you're following along with your pen and paper as well. Okay, James says he got it. Idris says he got it. Tarek got it. All right, fantastic. Okay, so let's look at this last portion here. It says the next network ID. So we know what the beginning of our network is and what the end of our network is. And we know what the creamy gooey filling in between is, which is our usable addresses. You're very welcome, James. So now to figure out what my next network is, where the next network actually begins, this is where this increment number comes into place. So that was this particular value that we spoke about here, which was the value 1. Now, it would be very easy if you looked at it and you would figure if the end of my network is 10.255.255.255, that once I add 1 to each octet, right, as it rolls over, that's why we did the exercises earlier, that if I'm incrementing by 1, the next network would have to be what? That actually would be the next network ID. Say that 3 times fast. Right? Can everyone let me know if they understood this piece? How we derive the increment? In essence, this is what we're looking at here. This is our first network. Since we have a /8, our network is only in the first octet. So if we're incrementing by 1, we're incrementing this number by 1. So this will be 11. Our next one, 12. And then in between them is what we calculated here, right, is this part. But the only way to do any of this was based on this, the subnet mask, the prefix length. Okay? So if everybody feels comfortable with this, I'm going to get into second gear, and we're going to look at an address that many people at times find very confusing. And that is because it does not break at what we would consider the actual boundary line. So meaning it's not going to be even 255s or so forth. So we're going to break this one apart as well. So we're going to look at the following now. We're going to look at 172.16.100.113. But it has a /12. Well, so if we look at it, right? So, Advan, I'm just going to briefly answer your question. Did this freeze? Just give me a second, guys. I think all right. So if we look at this table here, I'm going to show you. So this would be my /8. This would be my /7. This would be a 6, 5, and so forth. And if you see that, Advan, take a look. What would be my increment for 7? If we could actually use it, well, what would be my increment for 7? There you go, would be 2, right? So it's the same math over and over again. It doesn't change, irregardless of if I have a shorter prefix length, shorter subnet, which is basically the lower number that we call shorter, or I have a more specific or longer prefix, which means a larger number. The math is the same. All we're doing is we're breaking it up by actual positions. We're not going out and trying to calculate the entire 32 bits at once. We're breaking it up in 4 octets. So four sections of 8 bits each. So let me change this back. And let me just do this briefly. I'm not sure why. Okay, let's see. All right, so the first thing we're going to do on this one, I was just trying to see if something goes away. The first thing we're going to do here is we're going to now look at, and we're going to try to dissect 172.16.100.13. And what we want to do is we want to figure out all these values. What is our network ID? What is our valid IP address? And so forth. So the first thing we're going to focus on is trying to figure out 12 bits. Where does our network portion fall? Okay. So we know that each octet has 8 bits, 8 zeros and ones. In this case, it tells me I have 12 consecutive ones from left to right. So if I was to write that down, I would say 1, 2, 3, 4, 5, 6, 7, 8, dot. This will be my first octet. So I got 8 here. I need 4 more, which is 9, 10, 11, 12. As soon as I get here, I'm going to divide because I don't want to get confused, okay? But just so you know, here I'm in the first octet, and here I'm already in the second octet. But, exactly, Victor, it falls, Victor and Mick, correct, it falls in the second octet. But this one confuses a little bit because we have part of the actual octet being given to the network, and then the other part being given to the hosts. So for example, the remaining 4 bits here are set to 0. They belong to the host. And then, of course, the third octet is going to be set to all zeros when it comes to the actual prefix length. So that's what we're going to do. Okay, so I'm going to put this up here so that we don't get confused. And fourth octet right here. So the first thing now I want to do is, and we all kind of agreed on, my interesting octet is the second one. So I want to put that immediately in here. I don't want to forget this. This is very important. I don't want to forget it. I don't want to get confused. So that's where I'm going to put it. Next, I want to figure out what is my, well, in this case, we can probably also figure out the network portion, right? But let's figure out the increment first, because it's going to help in figuring out the network. So what is my increment? So I need to look at this particular section here, because those are my network bits, right? So as we said, the final network bit is my increment, right? So there's a few ways I can do this. I can go in here and I can just write down my actual values. And then I can find out this one is 16. That's one way I can do it, right? So I'm actually going to do this now. I'm going to add it in here as 16. Or what I can do is I can immediately jump towards the idea of trying to figure out what my subnet mask in dotted decimal is, which would include me adding these 4 bits together. And if we go back here on top, if I add 4 bits together, I get the number 240, and it tells me my bit value is 16. And that will be my increment. Okay? So that will be 240. Correct. That will be my actual mask. Now I'm going to do conversion. I'm going to take the first 8 bits. They are turned on. That would be 255. The next are turned on only the first 4 bits from left to right, which gives me a 240. First, this is the first octet, second, and then the remaining is set to 0. So let's not forget this. Let's add that in there. And now I'm going to give you guys a little bit of a way I orientate myself, just to give you an idea, because if you're doing this in your head, you kind of want to figure out a little bit of a shortcut in a sense. So when I look at this just makes sense to me. If it doesn't make sense to you, I'm sorry, but this is the way I orientate myself. I look at this. This is 4 bits, right? This makes up 4 bits. So I'm looking at this number and I'm saying like, every time from left to right, if I have 4 bits, my increment is 16. And then for some reason in my head, it popped in, it says 4 times 4 is 16. So anytime I deal with consecutive ones from left to right at the beginning of an actual octet, I know that 4 times 4 is 16. So I don't need to guess anymore. It sticks in my head. And if 4 times 4 is 16, now it's easy for me to remember that if I wanted to figure out what my mask is, if 2 to the 8th power equals 256, I can actually subtract 16 from 256, and I get the value 240. Again, I can actually verify my work. If I didn't know that this was 16, I can still take 256. I can subtract 240. Let's say they've been so generous and they gave you the decimal, dotted decimal format, and I know this is 16, which now I know is my increment. So as you can see, there's multiple ways to come to this conclusion that my increment is 16, that my mask value is 240. Does everybody understand this little shortcut? 4 times 4 is 16, and then I just memorize that 16 equals 240. And then the way we can actually come up with the various values, either the prefix length or the increment. Does that make sense so far? Right. If not, we'll discuss it more in the Zoom session, but let's move on for the time being. I'm going to it takes practice. Again, it's just patterns. The 4 times 4, I noticed was a pattern for me. 4 times 4 is 16. I got 4 bits. That's kind of just how I remembered it for myself. Okay. So my increment is 16. So if my increment is 16, now I know that the beginning of my network is going to be 172 because it has all ones. If I look at this piece right here, I know my first network can be 16. The 16 is, so this value 16 is derived based on the value of this binary position. So if you looked at this, the way this would look right now is we turned out the 128-bit, we turned out 128, 64, 32, and the 16. The remaining bits were set to 0 because they belong to the host. So because this is our most far right bit right here is the 16, this becomes our increment. Because that's where our network portion based on a subnet mask ends. So that's why our actual network ID would look like this. Based on this value. Does everybody understand that?
You know, Mark, let's come on screen. There's one other way that you can actually look at this funny math that I've seen be helpful. Chris, just bring us on for a second.
Yeah,
so,
give me your idea.
You know, Mark showed you the correct way to do it, where he added the bits. The other way you can look at it is 2 to the 4th power, which is 2, 4, 8, 16. And then if you were to take 256 minus 16, you're also going to get 240. Because at the end of the day, we have a total of 256. Now, when we add 1, 1, 1, 1, 1, 1, 1, we get all 255, right? But remember, we started counting at 0. So 0 all the way to 255 is a total of 256, which is 2 to the 8th power. By comparison, if you did 2 to the 4th power, you got 16. And then if you took the maximum of 256 minus 16, you'd still get to the 240. Likewise, if it was 2 to the 3rd power, because you had 3 bits, it would be an 8. And if you did 256 256 minus 8, you would get 248. And that would also give you the subnet mask of the 1 in the 128, 1 in the 192, and 1 in the 224. So, you know, there's lots of ways we can do the math. Mark's showing you the correct way, which is the way I want you to learn it. My brain does some funny connections in how it connects things. But at the end of the day, it's only 2 to an exponent of 2. So 2 to the 16th is, you know, that's 65,000 sort of range somewhere in there. But, you know, doing the math in your head. But just think of it that way. I think there's 2 ways you can look at it. I recommend Mark's way, but at the end of the day, it's all to 2 to the power of something. And if you can remember that, it's going to be much simpler.
Yeah.
Mark,
as a matter of fact, after this particular example, I'm going to show you a way that I would just go through it. Because it's going to go quicker, right? You're not going to have to sit down there. I'm still always going to recommend that you write out the mask and that you first in the beginning always practice where you put your dividing line and you learn what are my actual values. Like what would be the 4th bit position? It's 16, right? From left to right. But what if I gave you 7? What would that be? See, that's where I can quickly orientate myself. Well, I know 4 is 16. 3 more. So what am I looking at? I'm looking at 8, 4, 2. So I know it's 2. That will be my increment, right? So I'm going to show you after this one, though. We're going to move on to a /16, meaning 16 bits belong to the actual network portion. I'm going to show you quickly how we're going to run through that. And you're going to be like, what? I can do it that quickly. You can, but if you want to verify your work, this is the way you want to do it, and especially in the beginning. Like what Mike said, he picked up on the patterns, just like I did. 4 times 4 is 16, 16 to 40, right? But for example, if you can remember these 16 digits, right? The 16s, meaning from 1 to 128, from 128 to 255, that's all you need.
Yep.
And I'm going to show you as we go through it that they actually all repeat.
Yep.
That's another interesting part. So as long as you remember them, you can pretty much get any answer you want to in your head. So let's finish up this. Then I'm going to go to the next one. And I think Mike is going to enjoy that one because we're just going to breeze through it. And then we're going to add some requirements to it before we move on to the super netting. And then if there's more questions, we'll answer them on the Zoom session. All right. If you can go ahead, Chris, and share my screen again. All righty. So what we want to do is now we know what our increment is. We know what the beginning or the network ID is of our actual network. What we want to do next is simply figure out what is my broadcast IP. And if you guys recall from the previous example, and what I'm going to do, let me remove this now because it's going to be in the way for us to do some calculations. To calculate what my local broadcast IP, right? So this piece here is, I'm going to turn on, and let me remove this. I'm going to turn on all these bits, right? That's what we said. Just turn them all into ones, and then you get the idea. So, and this is where I said, now you have to be careful. Let me ask you this. If I turn on all these bits, what is the decimal value here? And I'm gonna cheat a little bit. I'm gonna show you this. This is, well, actually, let that go away and then I'll show you. This is, well, these are the values that we're focusing on in this section. So that would be, where's my pen again? Here we go. It would be 1, 2, 4, 8. What is 8 plus 4 plus 2 plus 1? If I'm turning all these bits on, these are the actual decimal values. What do I get? One plus 2 is 3, plus 4 is 7, 15. Fantastic, you guys got it. Now I'm going to show you a little trick. Something that can speed it up a little bit for you guys. Do you see the next bit, what its value is? It says it's 16, right? So if you ever find yourself in a situation like this, and I can demonstrate it right over there. Let's say I'm turning these bits on. Right, so I'm turning these bits on. I'm gonna quickly show you guys how easy this is. This is 1, 2, 4, 8, 16. My next would be 32. So if I added all these together, I would get 31. So you don't have to sit here and actually do it the hard way and do 8 plus 4 plus 2 plus 1. You simply look at the next bit, what its value is, and you subtract 1. And then the following bits, which in this case are these, would be 1 less than. That's another quick way you can do it. But to get comfortable, do it this way first. Okay, little tips that you guys get there. So let me remove this because this would not be accurate right now for this example. Okay. So if we turned on now the following bits, we would get 255. And if we turned on the remaining bits over here, we would also get 255. I'm not going to write the ones underneath it just for some brevity, but that's what it is. So now we got to look at this. This is my address as it currently stands. So To figure out what my last address is, as we said before, I have to take this value now, and since we're in the second position, I have to add it to this value of 16. Okay, and then 15 and 16 would give me the value of 172.31. And then the remaining values are 255. That gets added to the third. And 255 plus 0 is 255. And then in our fourth and final octet, 255 plus 0 is 255. And that would be our local broadcast address. But does everybody understand this piece here now? Because that's what throws people off quite a bit at first. And I'm going to show you a trick in the next one, how you can completely bypass this type of mess. But do you understand that currently how this works? If you did, type a yes. If no, let me know. And in the meantime, I'm going to clean up just a smidget. Okay, let's get rid of this. All right, fantastic. Okay, so now we're going to move on to this piece here, my valid IP range. No problem, sir, and you'll get it. You may have to watch your recording again, and you'll have to practice a little bit, but you will get this. This is, I'm showing you the ins and the outs of how to do the calculations. Next example, you're going to be shocked at how quickly this is going to go. Okay, so I want to focus now on trying to figure out what is my first valid IP address. I know what the beginning range, right? This is the beginning, this is the end is. I want to know what the next one is. And as we said earlier, the way to do it is I need to turn on the most far right bit to 1. Because we're still doing basic decimal counting at this point. So if I turn on this bit, again, this is this bit right here that we're talking about, the 2 to the 0 power, right, which is 1. My first valid IP address would be 172.16, and this is the fourth octet, right? So this is the fourth octet I'm dealing with. The third would be 0, and this would be a 1. And that will be our first valid or usable IP address that can be assigned to a server, to a firewall, to a printer, whichever you like, whatever devices you have. And then to figure out what our last valid one is, we're going to go through the same exercise. We turn on these 4 bits, which we agreed upon was 15, which is also 1 less than our increment. We're going to turn on all these bits, which gives us 255. But we're not going to turn on every bit in our last octet, but we're only going to turn on 7 of them, which provides us 254. So all we're doing is we're adding these together because that's where we turn the ones on. So my last usable address would be 172.16.31. You see, I made the mistake. I didn't add it. 31.255.254. See, even I have to be careful and not hurry. Why do we need to know all these calculations? Amalia, hold that question. What we'll do is we'll address it after the next example. Mike and I will address it. And what you might be pleasantly surprised that we might have a few different answers to that. So just hold on to that question, please. Okay. Let me just delete some of this information or remove it. Okay. And now you can go the long way, right? We said this was an increment of 16. So what would be the next network? If my first network is 172.16.0.0, I have a prefix length of 12, right? You can see it here too. I have an increment of 16, That means I'm incrementing in this octet, the second one. So what would be my next network based on simple math? I know we can't change this. This is not changing. And we're incrementing at 16. So what is 16 plus 16? Yep, that's it. So our next network would be 172.16.32, sorry, here, 172.32.0.0. Okay, so this was a little bit harder example, but I hope it showed some of the pitfalls that can happen, but how we can navigate them as well. So I'm going to move on to our next one. And what I want to show you guys is how we can drastically speed this up, this process of actually doing the calculations, trying to figure out what is my network address, my range, all based on the increment, okay? So let's do that. Let me pick up and, yeah, let's do this one. Okay. Okay, so the next network that we're going to be looking at is going to be the 192.168.44.100, and we have a prefix length of 16. So that tells me 16 bits belong to the network. So if I did some simple math, that would tell me I have 8 bits in here, I have 8 bits in here, 8 bits in here, 8 bits in here. So my network portion is actually derived from these 8 bits, which is 16. So I know right off the bat already that my network ID is going to begin with 192 and 168 dot something. I also know that based on that /16, the 16 bits, that my interesting octet is going to be the second octet. Because if I have 8 bits here, so let's take it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then the rest is going to be host bits. And this is my division. And then this at the 192, this at the 168. And that's how I know that this portion does not change. And this is also in the second octet. Okay? Everybody follow so far? All right, fantastic. Now I added the dividing line so that we have a visual. What is my bit value from this bit right here, the first bit to the left of the red line? One. Yep, that's it. So now I add it. Okay. So I now figured out this portion, which now tells me that my network actually begins with 192.168.0.0. So if my network, and this is now where you're going to accelerate, we'll show you how to do it. If this is my first network, I'm incrementing by 1. And we know it's in this case, we're incrementing where? It's going to be the second octet, right? So what's my next network? Okay, I'm just writing a couple of down for you guys so you see it. That's right, the second. So if I'm at 192.168.0.0, my next network is 192.168.9.0.0. So if this is the next network, if I go back 1, meaning the 0, I subtract 1, this is what I would get. The first octet wouldn't change, but my second octet would. I would go back to 168. And then what would happen to these? If I go from 0 back 1, what is the next largest number based on these values that I can calculate if all the bits are turned on? So we started at 1. It's 255, right? So that's what my local broadcast IP would be. So now what would be my range? And just so you guys understand, I'm not looking at this anymore at all. I'm simply looking at this over here. So if my network begins with this and it ends with this, now I can just fill in everything else. Okay, my first IP address is going to be 192.168.0.1. I can't use 192.168.255.255. I have to go back 1, which would bring me to this. Now that's it. We already now, without doing any complicated math, we simply maybe added or subtracted 1. We didn't stick back over here and say, okay, if I calculate all these give me 255, right? Or if I only turn on this bit, I get the 1. All this was calculated in that sense. And then finally, what is my mask? I have 16 ones, meaning I turn them all on in the first octet, which gives me 255. I turn them all on in the second octet because we have 16 bits, 255. The rest are off. And there you go. And that's how we completed this entire section. And that's with me explaining it to you all. So eventually, if you can figure out what your increment is, basically by what number does my networks go up, which gives me my current network and my next network, you can quickly figure out that, okay, my next network is this number. I go 1 back, which gives me the local broadcast ID of the previous network. I already know my network ID based on the actual taking a look at the subnet mask and finding out what my increment is. And then I fill in the creamy middle GUI. That's it. Do you guys have any questions so far about this? Otherwise, I'm going to move on to taking a look at what if you're being given a requirement of what we need to do.
Let's address one thing before we go to the next part, Mark.
Yes,
Maybe we
go ahead,
come on
please.
screen for a second, because we got to tune this for cloud computing. So the numbers Mark gave you are 100% accurate, and they are correct on every network device in the entire world, except for in the cloud. And they're still technically correct, but the cloud providers have automatically reserved certain addresses. So in that example that Mark gave you, let's say we have a 192.168.1.0/24 network. The network address is the 192.168.1.0, which you all calculated. The broadcast is 192.168.1.255, which you all calculated. And normally the range of usable addresses would be .1 to .254. However, the cloud providers reserve certain addresses. So if we're working with AWS, for example, the same 192.168.1.0 network address will still be reserved for the network address. Now, AWS reserves the .1 for the router in that subnet. So in that particular subnet, the 192.168.1.1 will be reserved for the AWS router. And AWS will also reserve the .2 for DNS purposes. So the 192.168.1.2 was reserved for DNS. And then AWS would also reserve the 192.168.1.3, and they're going to reserve that for future use. They don't know what it's for, but it's there for future use. And then, of course, they reserve the broadcast, the 192.168.1.255. So just keep that in the back of your mind. Normally, we lose the first one and the last one, the network and the broadcast. When we're dealing with AWS, they reserve the first three addresses and the last address, so we burn more. And why are we talking about this? Because normally speaking, we would use a /30 for a WAN subnet, point A to point B. We can only have two possible addresses. But on AWS or other clouds, we can't do that because they reserve three addresses. They reserve four addresses. So the smallest subnet we can use in cloud computing is a /28. Just keep that in mind.
Yep. And what we'll do is we're going to jump to the example where we're going to be given a requirement. And this is where we're going to do the longhand form so that we see the math behind it to understand how we get to that actual number, because this is the actual subnetting portion. What we've been doing so far is trying to figure out within this network that already somebody subnetted for us, what belongs to us? What is our network ID, which the router is going to use to determine what it is part of. Then we're going to have our local broadcast IP, which is basically a one-to-many communication for everybody on that same network. And then as well as our first and last valid IP address that we can assign. And like Mike said, the actual assignment and what is reserved and what is not reserved outside of the two IP addresses that we mentioned, which is the network ID and then the broadcast, is based on the use case. For example, I've generally set up any SD-WAN customers with reserving the first 13 addresses so that I can give one to the actual interface, and then the remaining ones were either given to anything specific that was part of the infrastructure. Could have even been server. And then the remaining IP addresses that we had were actually part of the hosts that they can use. So it's going to vary based on what your requirement is, on what IP address out of that valid range that you have. And those can also be different depending on how the network is subnetted and how you're going to use it and how you're going to reserve it.
Great. And to get to Amelia's question, I'm going to do something very quick. Chris, if you can let me share my slides here real quick. I want to just show an example of why this is so critical. So let's say we have an environment where we've got two routers. Very simple. This is a nothing environment. And we've got a link between the two routers. And on each router, we have an Ethernet segment, which is where actually let's make it, instead of two routers, let's just make it three routers with links to each other. I think that'll make it a little easier. We'll draw a third router. Now, how many host addresses can we have between this router over here and this router over here? Only two. But let's just say for arguments, we had a 1.0.0.1/8. And on the opposite side, we had a 1.0.0.2/8. And remember, every interface needs to be on a different subnet. So now on this side of the link, let's say we had a 2.0.0.1/8. And then on the far end, we had this 2.0.0.2/8. Now, if you'll recall, we have the number of hosts in this subnet would be 2 to the power of 24th, which basically means a lot of addresses that would be wasted. 65,000 in particular, actually, if I did the math correctly. So it'll be 2 to the 24th. So as you can see right here, we lost 2 to the 24th power of addresses on this side and 2 to the 24th power of addresses on the other side. Remember, we ran out of IP addresses a long time ago, so we've got to be careful on how we use them judiciously. We'll spend them wisely. But let's say by comparison, and Mark's going to get to this, if we used a /30 and we had 1.0.0.1 and 1.0.0.2/30, and then we had our next subnet, which began with 1.0.0.4, but we can't use that because it's the network, and we changed this to 5, and then we had the /30. Oops. 30. And on the opposite side, let me just get rid of this because I cut and pasted one too many times. And then we have 1.0.0.6/30. What we did is we used a total of 8 IP addresses in the process versus the 2 to the 24th power on each side of the link. And that's why we must do this. It's all about, and Chris, you can stop sharing my screen now. It's all about maximally using our IP addresses. Now, getting our IP addresses right, which is a more advanced concept, and how we design our subnets and how we architect them from a routing perspective, is the equivalent of the streets that are in a city. I'm sure many of you have been in a city that was designed in the 1600s, where they've got streets this wide and little cobblestones because it only had to fit a horse and buggy, which is the biggest thing that went down the street. Fast forward 300 years, and the city population went from 30,000 to 3 million. And now we don't just have a horse and buggy. We've got cars and millions of cars in the city and millions of motorcycles and millions of bicycles and millions of people walking. And you can see how that fell apart. Well, it's no different with our IP addresses and our subnet planning. If we get it right, it's going to be a city that runs smoothly. And if we get it wrong, it's going to be an absolute disaster. So we have to be very careful about our IP addressing. I hope both from a perspective of not running out of IP addresses, and the routers are going to use the subnets to actually calculate their routes. And if we get that wrong, everything falls apart. So Mark, I can go back to you. I just wanted to make sure we addressed that question while we were here. And Mark, you're muted. Between you and I and our mute buttons.
All right. I hope now I'm audible.
You are audible now, yes.
Fantastic. I was going to say is one of the most critical aspects of this, and you're going to see this also happening as you go through your journey of either becoming an engineer or hopefully, we hope that you become an architect. There's a lot more fun in that. You'll notice that the subnet mask is crucial. It reveals so much information to us that we can gather all this information just as we have there. If you want to remember something, though, remember those 16-bit values that we've given you, right? It'll be 1, 2, 4, 8, 16, 32, 64, 128. And then from left to right for the subnet mask, we want to remember 128, 192, 224, 240, right? We just added the values, 248, 252, 254, 255. That's all I remember. And then some shortcuts like 4 times 4 equals 16. But that's what you want to remember. Now, we're going to move on to the next example here. And what I'm going to do is I'm giving us all a requirement. And we need to actually now to perform subnetting. So this is going to be a form of a design discussion on how do we accomplish that. Now, what I'm giving you, is that very realistic? Not necessarily, but it will prove a point on how to perform the calculations in case you need it, and how we can take a predefined address space and chop it up into more smaller address space. And that's also going to address the question that Mick B had in regards to where the actual network portion works from left to right with consecutive ones, and where we look at from the host portions from right to left. So if you could, Chris, go ahead and please share my screen. All right, fantastic. Thank you so much. So the requirement that we were given here is that we have a 172.16.0.0/12 network. So this is not a new network. We've seen this before. But the difference is not going to be, we require 500 subnets. So how would we calculate that? So the first thing that we, again, need to do is we want to figure out, what does 12 mean? What is the increment for 12? So what I like to do, I like to break it down. Now, I know that the first 8 bits, meaning these, are not going to change. So I'm just going to write them down, right? I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. I need to get to 12, which is 9, 10, 11, 12. I'm going to draw my line. And then the rest, right now, the way we know it is host bits. And I'm just writing out the remaining octet. Okay. So far, it doesn't look any different than what we did before. And as usual, what we want to do is we want to figure out what is the increment over here so that we understand what are we starting off with. And as you've noticed, this is where my little shortcut comes in. I see there's 4 bits here. 4 times 4 is 16. That immediately tells me I can write this number down here. If I'm not sure, then I can start counting my bit values, which is 1, 2, 4, 8, and then finally 16. All right. So far, it's nothing different than what we've done before. This also helps us appreciate that, and I'm going to write it over here. Our network ID is 172.16.0.0/12. We know that because we never changed it up here. Our increment, we're going to write that down as well, if you're following along, is going to be 16. And if we wanted to add networks, I'm going to write it down as well. My next network would be 172. That doesn't change. Because of the /12, I'm only interested in the second octet. That's where I'm actually doing my incrementation, which means 16 and 16 gives me 32. And then if I wanted to, I can fill in the rest of the information in case I was interested in knowing what is actually the range of my network, including my first IP address, my last, including the local broadcast IP address. Okay, so far we've done nothing new. Now the question is, and this is now where something new comes in, the math doesn't change, but how we do it is going to be new, is how do we get to 500 subnets? Because right now, if I was to count how many subnets I'm capable of having, if I have an increment of 16, and again, networks are counted from left to right because of the ones that we see. I'm going to look at the octet where my last one is and only consider them. I already have a network, so if I added another one, it would be 2, 4, 8, 16. So 16 is the amount of sub-networks that I could create right now based on the 172.16.0.0/12 network address range that I have. And if you were to write it out, what you would notice, you would go 16, 32, 48, and you will get all the way up to eventually what you see to be your dotted decimal subnet mask, which in this case would be written as 255.240.0.0. You would get all the way up to this number. And if I do 240 plus 16, I'm 256, which means I can't do that. It means it's full. So that would be my last network, but that would give me 16. Which part would you like me to repeat, Adfont? All right, while I wait for that is, so networks from left to right, hosts from right to left. The number of subnets, yeah. So the way we do our math doesn't change, right? We're still bound by our decimal values, right? So this doesn't change. The only difference is when we're doing the counting of hosts and of networks. Now, assuming that we understand networks, we count from left to right because of the consecutive ones, and hosts we count from right to left all that matters is we need to understand we already have a network. This is our network. So when I calculate the value of this position, remember, I'm starting at the next value. I can't do 1, already have it. It'd be 2, 4, 8, 16. I can't get past this because this belongs to the hosts for now. But my math is still binary. I'm still doing multiplication by 2. But I want to know what happens as I add bits to it, bits that I turn on for the network. What will be my decimal value? And that starts at 2. And in the host part, there's something similar like that because we are reserving 2 addresses. Those eventually we will subtract from the total. And you'll see how we do that. But I just want to show you guys this part right now so you understand. This right now shows us, because we only have these bits available, on what would be our range that we can create of subnets. So we were tasked now though with 500 subnets. So this is where the concept comes in of actually using host bits. So we want to use these bits here. We're going to borrow them from the host portion so that we can create more networks. So in the chat, let me know what denotes a network based on binary language. Like, how do we need to denote it? Think about your subnet mask, aka your prefix length. We denoted it by a string of consecutive ones from left to right and checking it against the IP address of what was part of the actual network. So this is where the trick comes in now. Yes, I was asking the question, how do we know what is part of the network address? So that's what I was pointing for. We know it based on the ones from left to right that are in consecutive order. That's how we know that this is part of the network. And then we also know that we have consecutive ones here. So part of the second octet is also part of the network. And of course, we shorthandedly write it in the prefix length notation or CIDR notations, which is 12. So what our job now is, we need to borrow bits from the host portion, going from left to right, and add them to our network portion so that we can create an additional 500 subnets. So this is now taking a larger piece and carving it into smaller pieces. So our networks, while we're creating more of them, we're actually creating smaller networks now too. So the way this was look now again, we're going from left to right. The question is, how many bits do I need to take away from my host portion to come up with 500 subnets? And that's why I showed you guys the counting. The 2, the 4, the 8, and the 16. But I'm not going to count it here anymore because I own these networks, right? I own these bits. I don't care about them. I need new ones. So I'm going to look now at these bits. And I need to figure out how many am I going to borrow. So I'm going to go through the same exercise. I'm going to start counting from left to right. So if I take this bit, this is going to be 2. I can create another network. So 2. Next one is 4, 8, 16, okay? So far we're just doing basic binary, in decimal conversion where we're just moving up the numbers, we're multiplying it. Then my next bit value is 32. I'm going next to 64. So again, right? We're just moving these up. 128, and I'm going to move up here. And this is 256. So that's this bit, right? So now I'm at 256. So normally I always tell you guys this means we're full. But in this case, all I'm doing is I'm still borrowing bits. So I have to keep multiplying. So if I borrow the next bit, which is going to be this bit, 256 times 2 will provide me 512. And then if you keep going, of course, you go from 512, you times it by 2, which gives me 1024 and so forth. And that's how you keep incrementing. But this is what we just did. We just counted from left to right what we've done before, multiplying by 2, going 2, 4, 8, 16, 32, 64, 128, borrowing the bits from our host portion and adding them to our network portion. So we're borrowing exactly. And this is what we're going to count right now. We require to go up to this portion right here, which is 9, right? Because this is 4, 8, and then this gives me 9. So I'm borrowing 9 bits. So what I'm going to do, I'm going to write this over here, 2 to the 9th power, right? 2 to the 9th power. I'm borrowing 9 bits. And I'm going to change this up. I'm going to rewrite it because it's going to be my new network bit. So I got 1, 2, 3, 4, 5, 6, 7, 8, and I'm adding 1 more. Okay, and then the remaining bits remain the same. Okay, so does everyone so far see what I did there? I took from our hosts and I reassigned those bits by turning them on from left to right to our network portion. Type in the chat if you understood that part. Okay. So we verified through counting that we have now created the possibility of 2 to the 9th power of networks. So if you did the counting on your hand again in 9 bits, that would be 2, 4, 8, 16, 32, 64, 128, 256, and 512. So 2 to the 9th power is 512. So these are our subnets. And I had to borrow 9 bits because if I only borrowed 8 bits, I would not have met our objective. So I need to at least have had 500 subnets. And we were able to create 512 additional subnets. So we meet our minimum requirement. So our task is this now. Our mask or prefix length still remains the same. We need to update because our range has changed. So the way we do that is, again, we count the amount of bits we have. In this case, we agreed there was 9 bits. Well, those need to be added to the network portion. So simple math, 12 plus 9 equals 21. So we have now a total of 21 bits that belong to the network. So I would have to go up here and change this to a 21. And that would be our new network prefix or prefix length or subnet mask of 21. And that is subnetting for a subnet requirement of 500 networks. And then, of course, what you can do is you can go back. We won't do it right now for brevity's sake because we will go in a few other things. You can go back and calculate what is my first IP address, what's my last IP address, what would be the network range. But this will be a way to subnet a network based on a requirement. All right. Mike, if you're around, if you want to bring up back on screen.
Absolutely. Thanks, Mark. So this is really what goes into subnetting, how we do it, why we do it. You know, network architects like Mark are going to have to think about how many subnets they need to create. The average user is going to think about how many hosts they need to create per subnet. I'm going to give you some real secrets here. It's going to make your life real easy. Wide area networking links, always use /30s. Why? Because we can only have 2 hosts. So if we use the /30, we've got the 0, the broadcast, and 2 usable addresses. LAN links, give you another secret here. Typically a /24, and here's the reason why. If you think you only need 20 servers, I promise you it'll become 100, 150 or more. So give yourself 254. The biggest LAN subnet you can potentially use practically is a /23, because once we get bigger than a /23, which gives us about 500 addresses, 510, I haven't done the math in my head, 512 minus 2, so it's 510. But anytime we go beyond that, we have too many broadcasts. So /30s for WAN, /24s for LAN. And on the cloud, if we have a WAN link, we'll just do a /28 because it's the smallest link we can go. So, we talked about why we do subnetting. We talked about the ability to preserve addresses, the ability to conserve them, the ability to use just what we need and what we need it. Kind of like taking a pizza and chopping it up to the right sizes to feed your friends. Now, I almost would love to go through IP addressing, and supernetting, which is kind of some of the exact opposite, which we need to do when we connect to cloud computing. And we're going to need to do it because when we deal with the cloud and the cloud and networking, any cloud provider, we kind of about 20 years behind on the networking we can do in the cloud. In a regular Cisco router or a Juniper router or an Arista router, I may get 800,000 routes from the internet. But when we connect to the cloud provider, we can only give them 100. So we're going to almost have to do the exact opposite of this when we connect to the cloud. And we can also talk about IP addressing. So let me know if you want Mark and I to host a supernetting and more of an IP address planning webinar. If you want, Mark and I will do it. We love getting geeky. I'd say now's probably a good time to invite you all to Zoom. Mark and I will spend about 30 minutes with you, up to 45, no more than that, because my managers, and that manager means my cat and my wife, will both be ready to tell me that I've got things to do. So if you guys want a supernetting one, we'll do it. And we'll talk about IP address planning and where people break their cloud architectures and network architectures because they used a subnet calculator and they didn't understand what they were doing. So it sounds like, Mark, you and I got another fun workshop that we can run. We'll make it free.
We do.
It'll be.
I mean, I could realistically show you guys an example of supernetting in 5 minutes, but the way I would show it to you guys, you're definitely going to want a few more examples because I do not believe in any type of shortcuts when it comes to supernetting because of how important it is, especially if you own your address space and you got to let others know you own it. If you make a mistake, you could potentially be causing havoc on the public internet.
Absolutely.
So that's a little teaser for possible another workshop.
Yeah, and I got to tell you, in 25 years as a network architect, I'd say 90% of the problems I had were when they had someone that wasn't a network architect dealing with the IP addresses. They got the IP addresses wrong, which destroyed the routers. The routers couldn't handle the bad routing. They would crash, reboot, and then we had absolutely nothing. So why don't we do this? Everybody take 5 minutes. We'll join on Zoom at 6 p.m. I popped the link to the webinar, but I'm going to have, I'll make sure I do it again. Chris sent me the link to the webinar. We're just going to jump on Zoom, and that way you guys can ask questions and not be limited to a 200 or 220 character space in a chat box. Plus, I like meeting new people. I like seeing people, and it's nice to do it in a nice environment. So hope you enjoyed this. Give me a hashtag, AWS Networking Training, so I know that you were here and you had a good time. If you didn't like the video and you had a good time or learned something, please give it a like. Please subscribe to the channel, hit the bell to be notified of something else. Make sure you catch all those free resources that are in the description of this video. Webinars on how to get your first cloud architect job, for example. Books on how to get your first cloud architect job. Webinars on how to become an AI architect. Documents on the skills you need to earn more. It's all free. Take advantage of it. The link is in the description of this video. So I'll see you on Zoom in about 2 minutes, everybody. And actually, I probably should say today is the last day to take advantage of our 50% off of the new Generative AI Architect program designed by David Lithicum and me. It's something I'm super excited about. So join us. If you want more about that, we will tell you. And maybe my team actually sent me the link to that. Who knows? So see you on Zoom in a few minutes, everyone.
Hope you all can join us. I look forward to it.